What lies at the end of everything? When stars fade, matter decays, and even time begins to lose meaning, what remains? This is a glimpse into the universe's distant future, a trillion years from now, where speculation becomes the only map and reality may transform into something unrecognizable. But before we continue, subscribe to the channel so you don't miss out on any of these videos. We begin with the most widely accepted long-term fate of the universe: heat death. Heat death is not a dramatic inferno. It's not an explosion, nor an apocalyptic tear in the cosmic fabric. Rather, it's a slow, creeping stillness, a whisper rather than a scream. The name itself is misleading, as it doesn't involve heat in the fiery, energetic sense. It refers to thermodynamic equilibrium, the point at which the universe reaches maximum entropy. Entropy, the measure of disorder or randomness in a system, increases with every action, every reaction, and every transformation. In a system like the universe, which is vast beyond comprehension, entropy never decreases. It only grows, and eventually it dominates. To understand what heat death truly entails, we must consider the journey of the cosmos from its fiery birth to its silent grave. It began with the Big Bang, a moment of near-infinite density and temperature, where all the matter and energy of the universe erupted from a single point. The universe expanded rapidly, and within a fraction of a second, the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, took form. Matter condensed, cooled, and formed atoms, then stars, then galaxies. Now, over 13.8 billion years later, stars are still being born, though at a slower rate than in the early universe. Stellar nurseries still churn, black holes still spin, and supernovae still light up galaxies like cosmic fireworks. But entropy grows. Each of these processes releases heat and spreads energy outward, contributing to the eventual balance of energy across the universe. The second law of thermodynamics governs all of this. In any closed system, entropy will increase over time. The universe, considered a closed system, is bound by this law. Over billions and trillions of years, energy will become more evenly distributed. Stars will exhaust their fuel. No new stars will form. The universe will go dark, not all at once, but gradually, as galaxies lose their luster one by one. In a trillion years, nearly all stars we know today will have burned out. The most massive stars will have died in cataclysmic supernovae, leaving behind black holes or neutron stars. Medium-sized stars like our Sun will have expanded into red giants before shrinking into white dwarfs. These white dwarfs will radiate heat for billions, even trillions of years, but even they are not eternal. Eventually, they will cool and fade, becoming invisible, cold remnants known as black dwarfs. As entropy increases, the temperature differences that drive all activity, chemical reactions, biological life, even the movement of particles, will disappear. Without differences in temperature or pressure, nothing can happen. No work can be done. The universe approaches a state known as thermodynamic equilibrium. In this final state, everything is spread out, homogeneous, and motionless on a cosmic scale. The stars are gone. The galaxies have ceased to shine. The background radiation of the universe cools to near absolute zero, where atomic motion grinds to an almost total halt. This is heat death, a place where time seems to lose its meaning because nothing changes. The very idea of causality begins to blur, because without entropy gradients, there is no direction for time to flow. Everything remains in stasis. A universe full of particles, perhaps even black holes and dark matter, but with no structure, no contrast, no dynamics. Just a vast, frozen nothingness expanding ever further. But reaching this point takes unimaginable lengths of time. Long after stars die, planets crumble, and black holes evaporate, the universe still carries on, inching toward heat death. Even now, the universe is cooling. The cosmic microwave background radiation, once 3,000 Kelvin shortly after the Big Bang, is now just 2.7 Kelvin, a whisper of warmth in an otherwise cold expanse. This cooling will continue until it reaches equilibrium, a state where all parts of the universe are nearly the same temperature, indistinguishable from one another. Some black holes, those left over from massive stars or formed in galactic collisions, may still roam the universe in this era, but even they're not immortal. According to Stephen Hawking's theory of black hole radiation, also known as Hawking radiation, black holes lose mass over time by emitting particles. This process is incredibly slow, especially for large black holes, but given enough time, more time than has yet passed in the history of the universe, they too will disappear. When the last black hole evaporates, all that will remain is a dark, cold, empty expanse of weak radiation and elementary particles, barely interacting with one another. Yet, even this idea carries haunting questions. If entropy reaches a maximum, does time stop? Does consciousness, if any were to exist in such a far future, fade with it? Would some distant descendant of intelligence devise a way to escape heat death? Or is it an inescapable prison of silence and darkness? These are the kinds of questions physicists and philosophers ponder when considering the deep fate of the cosmos. Heat death represents the ultimate equilibrium, not just of energy, but of possibility. With no energy gradients left, the universe is effectively dead. And this death is not sudden. It's a slow, chilling, final breath that takes longer than we can comprehend. Longer than galaxies have existed. Longer than even our minds can reasonably project. It is poetic, in a way, that the same laws that gave rise to the stars, to life, and to everything we know are also responsible for the universe's inevitable end. The increase of entropy is the silent clockwork behind existence. It is not a malevolent force. It is merely the nature of the universe expressing itself with perfect consistency. So when we imagine the universe in 1 trillion years and beyond, we must begin with heat death. Not because it's the only fate, but because it represents the logical conclusion of the processes already underway. Every light that shines, every atom that collides, every galaxy that spins, all of them are steps toward this future. It's not a fire that consumes all, nor a bang that shatters creation. It is a whisper, an unwinding, a great stillness stretching across a cosmic graveyard, filled with shadows of what once was. And yet, even in the concept of heat death, uncertainty remains. What if entropy isn't the end? What if the decay of protons, the nature of dark energy, or the fundamental constants of the universe shift in ways we don't yet understand? Could the cold silence be temporary? Could it be just one phase in an eternal cycle? Or could something stranger still be waiting beyond the veil of entropy? We have theories, we have ideas, and one by one, we shall explore them. The universe, that grand expanse of stars and silence, does not merely march toward death, it drifts. It stretches, it breathes outward in silence, expanding with every passing eon. The Big Freeze, often spoken of as a sibling to heat death, brings into sharper focus the loneliness of this expansion. It is not merely about energy dispersing evenly, but about the universe itself pulling apart so relentlessly, so infinitely, that even light can no longer bridge the gulf between stars. In the beginning, expansion was fast, almost violently so in the era of cosmic inflation, just moments after the Big Bang. Then it slowed as gravity tried to pull everything back together. For a time, it seemed possible that expansion might even stop or reverse. But then, around 5 billion years ago, something strange happened. Expansion began to accelerate. This mysterious force, known as dark energy, took over as the dominant component of the universe. And since then, the fabric of space has been stretching faster and faster, not slowing down but speeding up. The Big Freeze is the cosmic result of that runaway expansion. It's not marked by a dramatic collapse or a cosmic rupture, but by a cooling universe stretched to its limits. Galaxies are not just drifting apart. They are accelerating away from each other. and not just slowly. Eventually, the space between galaxy clusters grows so fast that light from one can never reach another. Entire regions of the cosmos become completely causally disconnected, unable to influence or observe each other. The observable universe shrinks, not in size, but in content. In about 100 billion years, most galaxies outside our local group will have moved so far away and so fast that they will become completely invisible. Even their ancient light will no longer be able to reach us. The universe will not appear filled with billions of galaxies as it does today, but only with the fading embers of those few gravitationally bound to us. By 1 trillion years, this isolation reaches a haunting crescendo. Star formation has already stopped. It ceases long before the trillion-year mark because the raw material, hydrogen and helium, is no longer plentiful in usable form. The great stellar forges grow quiet. With no new stars born, the night sky begins to fade. Stars like our sun that once shone for billions of years have by then lived, died, and faded into white dwarfs or black dwarfs. Massive stars exploded long ago, and their remnants, neutron stars and black holes, drift in silence. In this trillion-year-old cosmos, temperature becomes the tyrant. With no heat-producing stars, no thermonuclear reactions, and no energetic galaxies colliding, the universe drops in temperature. Slowly, inevitably, it cools toward absolute zero. Not all at once. Cooling happens at different scales and paces, but gradually, on average, the cosmos becomes a colder, darker place. Photons still exist, but their energy is stretched by the expansion of the universe. The wavelength of each photon increases as space expands, a process known as redshifting. Over time, even the background radiation, once the afterglow of the Big Bang, then a gentle whisper at 2.7 Kelvin, becomes unimaginably cold. The average temperature of the universe approaches absolute zero, and the light that once filled space with warmth now carries barely any energy at all. Entropy continues its silent climb, and the Big Freeze tightens its grip. In this frozen desert, particles rarely interact. Collisions become infrequent. Atoms drift through space without disturbance, sometimes for entire galactic revolutions. Dark matter, if it exists as hypothesized, continues to haunt the universe as an invisible scaffold. But it too provides no warmth, no energy. Just gravity, silent, persistent gravity that binds what little matter remains in cold, dead clumps. Some might imagine this future as empty. But it's not. It's just quiet. Ghosts of galaxies still exist. Dead stars still spin. Black holes lurk invisibly, warping space-time. But everything that once made the universe vibrant, the birth of stars, the creation of elements, the dance of planets, the chance for life, is gone. Over time, the expansion becomes so extreme that even gravitationally bound systems begin to feel the strain. Although local structures like our galaxy might remain together for a long while, expansion continues at such a pace that distant galaxies are not just hidden from view. They're unreachable in principle. Not even a spaceship traveling at light speed could ever reach them. The distances between celestial bodies increase faster than information can travel. This creates a deeply haunting consequence: cosmic isolation. Entire galaxies become lonely islands, never again able to see or communicate with any other. Civilization, if it still exists in any form, finds itself not only in a universe without stars, but in a universe without neighbors. The night sky becomes empty, not just dim, but truly blank. No galaxies, no nebulae, no supernovae, just cold space. Eventually, even atomic decay might slow and stop, assuming protons are stable. But if proton decay is real, a theory we will explore later, then even the atoms themselves begin to disintegrate over enormous timescales, turning matter into energy in the form of low-energy radiation. But even if protons don't decay, the outcome is the same. The energy within the universe gets stretched so thin by expansion that there's no longer any means for structure or warmth to exist. The Big Freeze is, in many ways, a narrative of exile. It is the slow banishment of matter from matter, light from light, and structure from structure. The universe doesn't die in violence. It is forgotten by its own parts. Every galaxy, every star, every atom slowly loses its ability to touch the rest. And in 1 trillion years, that exile is nearly complete. This future is cold not just in temperature, but in spirit. The interconnectedness of the cosmos that we see today, the gravitational dances of galaxies, the glowing filaments of galaxy clusters, the delicate balance of stars and gas clouds, is replaced by silence and distance. It is a cosmic loneliness so profound that it defines not just the physical reality, but the very concept of existence. From a human perspective, it is staggering to imagine. We live in a universe where we can still see billions of light years in every direction. Our telescopes reveal ancient galaxies, distant quasars, and the afterglow of the Big Bang itself. But in the Big Freeze future, none of this remains. There are no lights to see, no signals to hear, no movement to trace. Only the vast, ever-growing darkness between dwindling remnants of matter. And so, while the Big Freeze and heat death are similar in that both represent thermodynamic ends, the Big Freeze emphasizes the expansion-driven isolation of cosmic structures. It speaks of the void not just as a place of maximum entropy, but as a place where entropy grows because every object is being pulled away, every possibility stretched thinner and thinner until no event can ever link to another again. 1 trillion years. A time span so vast that our entire species, all of recorded history, the rise and fall of planets and civilizations, will be a blink by comparison. And yet, by then, the universe has only settled into its cold stillness. It will remain so for quintillions of years more, perhaps eternally, if dark energy continues to drive expansion at an accelerated pace. There are no explosions here, no sudden collapses, no cosmic calamities, just a slow drift into quiet, the last whisper of cosmic warmth drawn out until it vanishes. This is not a universe that ends with a bang, but one that continues in silence, so silent that it outlasts even memory itself. But some wonder, is this truly the end? Or is there a deeper unraveling at work, a hidden instability beneath the icy fabric of space? Because there are other theories, some stranger, some more violent, some more hopeful. And one of them suggests that the universe's story doesn't end in cold silence, but in collapse, transformation, or even rebirth. When you're ready, we will journey into those possibilities. Black dwarfs, once white dwarfs that shone faintly with residual thermal radiation, are among the final evolutionary states of stars. After billions to trillions of years of gradual cooling, white dwarfs lose their faint glow and become cold, dark, and invisible to the naked eye or any traditional means of detection. By the 1 trillion year mark, the universe may host countless black dwarfs, silent, frozen monuments adrift in an ever-expanding void. These stellar relics contain the dense, degenerate matter once illuminated by nuclear fusion, now muted by the immense passage of time. The black dwarf era represents a universe devoid of light from conventional stars. Star formation has long ceased. Galaxies have become skeletal frameworks of dead stars and remnant objects. And the sky, if it could still be seen, would lack the speckled beauty familiar to us. Instead, darkness would reign, pierced only occasionally by the rare cataclysmic event among ancient stellar corpses. Yet even black dwarfs are not eternal. Some physicists speculate that quantum tunneling may allow for rare, sporadic events within black dwarfs, such as spontaneous thermonuclear explosions after unfathomably long timescales, on the order of 10^1500 years. But by 1 trillion years, the conditions are not yet ripe for such extraordinary phenomena. Instead, these objects drift silently, locked in frozen inertia, their atoms slowed to a crawl, their structure preserved only by quantum pressure. Around this time, Gravitational interactions between black dwarfs and other objects, like other black dwarfs, neutron stars, or surviving planets, might continue, albeit slowly. Some black dwarfs may be flung from their galactic halos, exiled to the intergalactic wilderness where they remain alone for eternity. Others may fall inward towards central black holes that dominate galactic cores, offering the occasional merger or consumption event. These rare interactions are some of the last dynamic acts in an increasingly static cosmos. As the universe continues to expand, the distance between objects grows ever larger. Even the gravitational dance among black dwarfs becomes rare, then nearly impossible. Eventually, gravitational interactions become inefficient across vast chasms of space. Black dwarfs, though massive and dense, exert virtually no meaningful influence on anything else due to their isolation. They exist in solitude, drifting in a universe that is no longer a stage for stellar drama, but a graveyard of cosmic history. Their interiors remain strange, ultradense, mostly carbon and oxygen nuclei locked into a degenerate lattice. The matter inside is squeezed so tightly that it is more like a single, enormous atomic nucleus than any earthly solid. And though they are cold and dead by our standards, they still contain entropy, fossil records of the once vibrant thermodynamic chaos of stars. They are husks of complexity, decaying only slowly, in a universe where complexity itself is in retreat. If observers could somehow exist in this age, perhaps as advanced artificial intelligences or post-biological beings adapted to entropy-rich environments, they would see the black dwarf era as a monument to entropy. Nothing new is created. No warmth radiates. No life stirs. There are only the remnants, the slow, quiet sigh of the universe exhaling the last vestiges of its former self. As black dwarfs dominate the scene, the rest of the cosmic landscape continues to fade. The last red dwarfs, those tiny fuel-efficient stars that burned for trillions of years, are finally extinguished, joining their siblings in darkness. The cosmic microwave background has redshifted to such long wavelengths that it carries barely a whisper of its original energy. Even the background radiation that once defined the universe's thermal state becomes irrelevant. The darkness deepens. Still, despite their coldness and darkness, black dwarfs hold within them the memory of fusion, the memory of brightness. They were born from stars like our sun, stars that lit up planets, hosted life, and fueled the cosmic engine. Now, these remnants are tombstones scattered across an expanding wilderness. Each one is a fossil, a relic, a silent chronicle of thermodynamic evolution. The black dwarf era could persist for quadrillions of years, perhaps longer than the age of the universe, so far by many orders of magnitude. The universe has entered a phase not just of cooling, but of terminal simplicity. Structures no longer evolve, but degrade. Time itself, while continuing its linear march, seems devoid of new milestones. The future holds no bright novae, no stellar nurseries, no galactic collisions in the way we understand them now. It holds only the stillness of a universe that has used up its creativity. And beyond this point, what remains? Perhaps the slow process of proton decay, if such a thing truly occurs. Perhaps black holes, still lingering and slowly evaporating. But within this black dwarf epoch, the universe is both ancient and exhausted, a place where the light of creation has been extinguished and only the embers remain. If protons are not truly stable, as some grand unified theories suggest, then the universe is not only destined for darkness, but also for complete disintegration at the most fundamental level. In a reality governed by proton decay, the matter that makes up stars, planets, black dwarfs, and even you and me does not persist indefinitely. Instead, it slowly erodes as protons, the building blocks of atoms, decay into lighter subatomic particles over incomprehensibly long timescales. Although the half-life of a proton is still unknown, and no direct evidence of its decay has yet been observed, many theoretical frameworks estimate that if it occurs at all, it happens on timescales of at least 10 superscript 3 years. But by the 1 trillion year mark, a mere blink in that broader timeline, the first inklings of proton instability may already have appeared in isolated, extremely rare events. A black dwarf, already invisible and inert, might lose a proton here or there in its atoms. Over time, this loss becomes exponential. As protons decay, atoms cease to be. A single proton's decay might produce lighter particles, perhaps positrons, neutrinos, or even photons, depending on the decay path predicted by the underlying physics. Neutrons, composed in part of the same quarks as protons, follow suit. The electrons that once orbited these now-dead nuclei no longer have an anchor and drift off as free particles. Chemistry becomes impossible. The periodic table, once the foundation of the material world, becomes meaningless. By this stage, the black dwarf remnants, once monuments to stellar life, begin to dissolve into a fog of particles. The structured matter of the cosmos, already silent and dark, is now fading into non-structure. The decay is not violent. There are no explosions, no cosmic fireworks. It is quiet, gradual erosion, entropy winning the final argument over structure. The proton decay scenario reshapes the very notion of what the future holds. While black dwarfs and neutron stars could have theoretically lasted until far after the current age of the universe, their degradation via proton decay ensures their eventual end. The cold, inert stars become clouds of non-interacting particles. Even planets, long since frozen and lifeless, break apart at the subatomic level. Molecules disintegrate. Solids dissolve into radiation. Gas clouds vanish into fundamental particles. The scenery of this epoch is haunting. There are no stars to light the sky, no planets to orbit them, no atoms to form even the simplest materials. The universe becomes a vast, sparse fog of leptons and radiation. It is not merely dark and cold. It is formless. What exists is not structure, but entropy itself. Where galaxies once spiraled and stars once burned, there is now only a scattering of energy-bearing particles, each moving through space without interacting meaningfully with the others. This breakdown changes the way we perceive the arrow of time. Before, time was marked by processes, galaxy formation, supernovae, black hole mergers. Now, time is marked by statistical noise. A proton decays here. A neutrino glides endlessly there. The universe no longer hosts events. It simply exists, an inert stage devoid of actors. And yet, this entropy-rich state still holds information in a twisted, diminished form. The particles released by proton decay contain entropy and, in a sense, memory, though they may never again be reassembled into atoms. And though their energy is diluted to insignificance across an expanding cosmos, they remain footprints, imprints of what once was. They carry the ghostly echo of structure, long disassembled. For observers, if any remain, whether biological, synthetic, or otherwise, this is a deeply alien universe. The familiar forces still exist, but their effects are meaningless. Gravity no longer binds, because mass itself is disappearing. Electromagnetic interactions cease to matter because there are no stable atoms to support them. The strong and weak nuclear forces become irrelevant as nuclei fall apart and never reform. Physics, as it shaped the early universe, is still technically in place, but no longer relevant to what exists. It is a paradox, a universe full of laws, but empty of law-driven complexity. A cosmos rich in space, but impoverished in meaning. Temperature gradients, once the engine of motion and transformation, are gone. Everything moves, but nothing happens. Entropy is not merely high, it is total. By the time protons have mostly decayed, over the course of an unimaginable expanse of years, matter becomes radiation. Light that will never again illuminate. neutrinos that will never again interact, electrons that wander endlessly. This is the true dissolution of the material universe, not in fire, nor in ice, but in dispersal. This moment in cosmic history, if we can even call a moment, is the quiet burial of all form. Planets have already frozen. Stars have already faded. Now, even the idea of a thing ceases to apply. There are no more objects in a universe, only fields, quanta, and expanding space. And so what remains? What structure can arise from such complete dispersal? Perhaps nothing. Perhaps this is the end of physical narrative, a blank screen with no film left to play. But some theories offer continuation even here, stretching beyond the death of matter itself, into the strange, unsettling territories of black holes, dark energy, and even the bizarre creatures of quantum improbability. The era of proton decay is not merely the death of stars, it is the death of matter. It is the end of the cosmos as we understand it, reducing all known forms of existence to subatomic haze. It is the triumph of entropy over complexity, of silence over structure. But this is not yet the end of our journey. The Big Rip represents one of the most dramatic and cataclysmic visions of the universe's ultimate fate. In this theory, dark energy, the mysterious force driving the accelerated expansion of the cosmos, doesn't remain constant, as many models assume. Instead, its intensity grows. Over time, this escalating repulsive force begins to challenge and then surpass all the fundamental forces that bind the universe together: gravity, electromagnetism, even the strong nuclear force that holds atomic nuclei intact. At first glance, 1 trillion years may seem distant enough that the Big Rip, if it were to occur at all, would happen long after this point. However, in a model where the strength of dark energy increases rapidly, the timeline collapses inward. Trillions of years may be more than enough for the fabric of reality to begin unraveling. Initially, the acceleration driven by dark energy simply pulls galaxies further apart. That's what we observe today. Galaxies receding from each other at increasing velocities. But in the Big Rip scenario, that expansion doesn't plateau. It compounds, speeding up in a runaway process that feeds on itself. Every billion years, the repulsion grows stronger. The spaces between galaxies stretch wider. Then, crucially, the space within galaxies begins to stretch. Gravity can no longer hold them together. Imagine, for a moment, a future observer orbiting the supermassive black dwarf remnants of a once great galaxy. Suddenly, they notice something strange. The stars in the night sky begin to drift apart. Not slowly, as they might due to typical galactic motion, but quickly, as though some invisible tide is pulling them apart. It's not a storm. It's not a gravitational anomaly. It's the very expansion of space accelerating at such a rate that it's physically overcoming the mutual gravitational bindings of the stars themselves. Galaxies lose cohesion. Clusters fragment. Stars that were once gravitationally locked into a swirling dance are sent hurtling into darkness. Their orbits fail, their bonds break, and the sky empties, not gradually, but with terrifying rapidity. Eventually, the effect deepens. It begins to act on individual solar systems. The gravitational bonds that hold planets in orbit around stars weaken. In real time, perhaps within a human lifetime, planets drift from their stars, flung out into the cold abyss. But it doesn't end there. The force of dark energy continues to increase, now challenging the structural integrity of stars themselves. Nuclear fusion ceases not due to lack of fuel, but because the particles that form atoms are physically torn apart. Electrons are ripped from atomic nuclei. The nuclei themselves are split, not by energy delivered in the form of a collision, as in a particle accelerator, but because space itself is stretching faster than the strong nuclear force can compensate. It's as if the cosmos is caught in an ever-tightening vice of repulsion. The fabric of space-time doesn't just expand, it disintegrates anything within it. No force is spared. The electromagnetic bonds that form molecules, the nuclear bonds that form atoms, Even the gravitational relationships between black holes and their surroundings. None are immune. Eventually, nothing can withstand this escalating force. Black holes, once thought to be the last surviving structures in the cosmos, are not immune either. As space expands around them faster than the speed of light, their event horizons begin to evaporate, not through Hawking radiation, but through disconnection. They no longer hold anything because nothing can stay within reach. By the time the Big Rip enters its final phase, the destruction occurs not across billions of years, but within seconds. The very atoms that form matter are torn apart. Quarks, gluons, and leptons, what physicists currently understand as fundamental particles, are sundered. Space itself loses the ability to support structure. Observers, if any remain, would not witness this as a slow dissolution. It would be a final, blindingly fast disintegration of all things. Every form of matter collapses. The laws of physics, once rigid and dependable, are no longer enforceable. The universe becomes unrecognizable. Then it becomes undefined. There is no after in the traditional sense. The Big Rip doesn't just end the universe. It erases the very possibility of structure, order, or coherent space-time. There is no place left for events to happen. No field remains for particles to exist within. No energy remains that can be transferred. The final state is not cold, or dark, or empty. It is nothing, not void, but non-being, and in not just to things, but to the capacity for thingness at all. Time, too, is consumed in this process. Without a structured space-time to define it, time loses meaning. The arrow of time, so long driven by entropy and cause and effect, can no longer function when effects cannot exist, and causes have no framework in which to operate. The clock doesn't just stop, it dissolves. And yet, this scenario, extreme though it is, remains theoretically possible within certain interpretations of dark energy. If dark energy is not a constant, but an evolving entity, one that gathers momentum like a cosmic avalanche, then the Big Rip is its terminal point. But the universe is not limited to one possible future. There are other theories, other possibilities that await exploration. The Big Rip is a violent end. Others are more passive. Some are even cyclical. And some challenge the very idea of an end itself. In the unimaginable stretch of cosmic time known as the Dark Era, the universe sheds its last flickers of starlight and becomes a realm governed by the slow decay of remnants. By the time this epic unfolds, trillions upon trillions of years from now, every star will have exhausted its nuclear fuel, every planet long since frozen, and every galaxy scattered beyond perceptual reach. The cosmic tapestry will no longer be woven with vibrant light and color, but instead composed of ancient cinders, black dwarfs, neutron stars, and black holes. These silent monoliths drift through an eternal twilight, untouched by creation or change. No new stars are born. No nebulae paint the sky. The atoms themselves may have decayed into simpler particles, reducing the once rich universe to a sparse, invisible ocean of electrons, positrons, neutrinos, and photons with wavelengths so long they carry almost no energy. The temperature of the universe approaches absolute zero, an asymptotic descent into infinite coldness where motion itself becomes rare. Photons, once the messengers of life and energy, stretch to such long wavelengths due to redshift that they become incapable of interacting with anything. Darkness here is not just the absence of light. It is a deeper, more profound concept. The death of activity, the freezing of causality. Nothing evolves, nothing interacts meaningfully, and the very idea of time begins to lose its relevance. Without change, time has no reference. Clocks do not tick. The few remaining particles drift silently, each isolated by astronomical distances, never again to collide. The entropy of the universe reaches its maximum, a state of thermodynamic equilibrium in which all usable energy is expended and no further work can be extracted. This is the true quietus of the cosmos. In this era, the black holes left behind by earlier epochs may still dominate the gravitational structure of the universe. But even these titanic objects are not eternal. Over unimaginable timescales, 10 superscript 1 years and beyond, they slowly evaporate via Hawking radiation, releasing their stored mass energy as faint heat until they, too, vanish. With their departure, all gravitational anchors are lost. Space becomes geometrically flat, emotionally sterile, and utterly mute. No echoes of planets or civilizations remain. Only the faint background whisper of entropy, radiation without origin or destination, spreading into the infinite vacuum. The Dark Era is not just a phase of cosmic aging. It is the final veil, the last page of a vast book written in light and gravity, now closed forever. It is the ultimate isolation, where not even the memory of starlight remains. In the vast abyss of the far future, long after the lights of stars have extinguished and galaxies have been torn apart by expansion or entropy, the black holes remain, immense, enigmatic, and silent. These titanic remnants of stellar collapse and galactic evolution become the rulers of a cold and barren cosmos, a period known as the black hole-dominated universe. By the 1 trillion-year mark, most stellar activity will have long ceased. The last red dwarfs, those ancient, slow-burning stars, will have used up their fuel and dimmed into obscurity. White dwarfs will have faded into invisible black dwarfs. Neutron stars will cool and drift. But black holes, with their monstrous gravity and unseeable depths, will persist. They will be the dominant structures of mass and energy, shaping the cosmos not through light, but through warps in space-time. Supermassive black holes, millions to billions of times the mass of the Sun, will be scattered throughout the universe, remnants of galactic centers that once hosted blazing quasars and swirling accretion disks. Many will have grown even larger by devouring gas, stars, and even other black holes during earlier epochs. Over time, gravitational attraction may cause these giants to drift toward one another, coalescing into even more massive entities. These mergers will unleash powerful bursts of gravitational waves, ripples in the fabric of space-time itself. But even these cataclysmic collisions will gradually become rare as distances between black holes grow due to cosmic expansion. Eventually, each black hole may find itself alone, drifting through an empty universe, unable to reach or be reached. Even the reign of black holes is not eternal. According to the theory proposed by Stephen Hawking, black holes emit a slow and steady trickle of particles known as Hawking radiation, a quantum effect that causes them to lose mass over time. For small black holes, this evaporation process happens relatively quickly, perhaps in mere trillions of years. But for the colossal supermassive black holes, evaporation is an excruciatingly slow affair. Some may survive for 10 superscript 1 years or more before finally vanishing into a puff of radiation. At the 1 trillion year point, many black holes will still be present, cold and isolated, reigning silently in a universe devoid of light and life. They will outlast the stars, outlast the planets, and perhaps outlast all memory of what came before. In this era, gravity continues to shape the silence. These cosmic voids are surrounded by ever-expanding darkness, but their presence is still profound. They influence the trajectories of remaining particles, distort space-time, and contribute to the gravitational web that subtly links the dead universe together. Yet there is no one left to observe them. No telescopes to measure their spin or mass. No intelligence to wonder at their age or formation. The black hole-dominated universe is majestic in its stillness, a final chapter of cosmic structure before even the strongest bonds dissolve. When the last black hole evaporates, whether in trillions, quadrillions, or googol years, it will signal the end of form itself. The last vestige of complexity, the final monument to gravity's sculpting power, will be gone. As we move further into the theoretical future, beyond trillions of years, into a time so distant it becomes nearly abstract, we enter the realm of quantum probability and philosophical paradoxes. Among the strangest yet intriguing concepts proposed to explain consciousness and the arrow of time in such an ancient universe is the Boltzmann brain theory. This theory doesn't arise from astrophysics alone, but from thermodynamics, statistical mechanics, and a deep contemplation of entropy in a seemingly empty cosmos. Named after physicist Ludwig Boltzmann, it proposes a counterintuitive yet mathematically plausible idea that consciousness could emerge spontaneously from random fluctuations in an otherwise uniform entropic universe. In the far future, when stars have died, black holes have evaporated, and matter itself has decayed, the universe becomes a vast sea of near-perfect equilibrium. Everything is maximally disordered, and yet, in this immense, mostly featureless state, randomness still exists. Quantum fluctuations, tiny, spontaneous changes in energy or configuration, can occasionally cause brief, localized dips in entropy. Over immense spans of time, these fluctuations might assemble particles in highly specific configurations, even recreating complex systems like molecules, brains, or, in the most bewildering possibility, an entire self-aware mind. This is the essence of the Boltzmann brain hypothesis, that in the distant future, a disembodied consciousness, one with fleeting awareness and possibly memories, could arise momentarily from the quantum chaos of deep time. It would not be born, nor would it learn. It would simply be fully formed, existing for a fraction of a second before dissolving back into the thermal noise of the cosmos. And in a universe where time stretches infinitely, such occurrences could, in theory, happen endlessly. These minds might think they lived in a vibrant, star-filled universe, experiencing sensations, thoughts, or memories that never truly existed, all a product of randomness. This concept challenges not just our understanding of the far future, but also our understanding of ourselves. If Boltzmann brains are statistically more likely in a high-entropy universe than the emergence of life in a low-entropy one, then logically, one might argue we're Boltzmann brains, momentary illusions formed from nothing, deceived into believing we have a past, a world, a cosmos. The implication is unsettling. It suggests that the ordered universe we experience may be less probable than a hallucination formed by chance. However, many scientists and philosophers reject the Boltzmann brain scenario as fundamentally flawed or at least paradoxical. If most observers in the universe are random fluctuations rather than beings with evolutionary histories, then our entire experience of science, reason, and memory becomes unreliable. Any theory that predicts such a situation is likely internally inconsistent. After all, why should randomness lead to intelligibility or to a coherent understanding of physical law? Still, the idea persists because it arises naturally from equations that describe entropy and statistical mechanics. As the universe ages into hundreds of trillions, quadrillions, and eventually into ages unmeasurable in conventional terms, the conditions become more suitable for such phenomena. The backdrop is a dark, cold void filled only with low-energy photons, wandering neutrinos, and maybe the remnants of hypothetical dark matter. In this setting, with no stars, no planets, and no life, the occasional appearance of a Boltzmann brain would be the only flicker of complexity. One of the strangest implications of this theory is the isolation of such consciousness. A Boltzmann brain, by definition, is a solitary fluctuation. It cannot interact with other minds, communicate, or observe anything real. Its perceptions, if it has any, are self-contained simulations, unconnected to any external environment. This leads to the idea of existential solipsism on a cosmic scale. Minds born without context, living for milliseconds, and vanishing without ever knowing if they were real. Could a Boltzmann brain exist long enough to ponder its own nature? Could it theorize about the universe, question its origin, or experience emotion? These questions drift towards science fiction, yet they remain grounded in legitimate physical theory. The mind, as we know it, is an emergent property of a complex system. if that system can be randomly recreated in full detail. Even for a moment, consciousness might follow. But this version of consciousness would be surrounded by infinite silence and endless nothingness. From a practical standpoint, the likelihood of such a scenario occurring in our observable reality is low, but in the full stretch of an infinite, ever-aging universe, even extraordinarily improbable events may eventually occur. In 1 trillion years, perhaps only one Boltzmann brain might flicker into being. In 1 trillion years, there may be thousands, or maybe none at all. The universe, by that point, will be so dilute, so empty, and so far removed from the energetic conditions that once birthed stars and galaxies, that even the rarest of quantum events could stand as monumental. Despite its weirdness, the Boltzmann brain theory serves as a philosophical mirror. It challenges assumptions about time, experience, and existence. It invites us to consider whether consciousness is a fundamental part of the universe or simply a temporary glitch in a sea of noise. It redefines what it means to exist, to observe, and to believe we are real. Perhaps in that distant epoch where black holes have fizzled and entropy reigns unchallenged, the only witnesses to the universe's fate will be these ghost-like minds. They won't build civilizations. They won't record history. But for an instant, they might think, and in that fleeting moment, they might remember a universe long gone. In this lonely, decaying cosmos, the Boltzmann brain is not a new form of life, but a final echo of structure in a world ruled by chaos. A last whisper of thought in a place that has forgotten light, heat, and time. The legacy of all things, reduced to brief sparks of self-awareness flickering through the eternal dark. In stark contrast to models of permanent expansion or ultimate decay, the cyclic universe theory offers a radically different vision of cosmic destiny, one where time itself may not be linear, but recursive. According to this hypothesis, the universe may not be heading toward a single irreversible end, but instead participates in a never-ending sequence of births and rebirths. Each cycle involves expansion, evolution, decay, and eventually collapse, only to be followed by another Big Bang, resetting the cosmic stage. At the heart of the cyclic model lies the idea that the current phase of accelerated expansion we observe is just a chapter in a much longer epic. After 1 trillion years of growth, galaxies may have receded beyond detectability, stars may have gone out, and entropy may have peaked. Yet this bleak scenario might be nothing more than a transitional state. Instead of stretching infinitely toward emptiness, the universe may begin to contract, reversing the very process that started it all. Gravity, dark energy, or other unknown forces might tip the balance and trigger a slow but steady collapse. This eventual collapse, often called the Big Crunch, is envisioned as the mirror image of the Big Bang. Matter compresses, space contracts, and temperatures rise. Galaxies fall back toward one another, black holes collide, and time as we understand it begins to blur. In this high-energy, high-density environment, the seeds of a new universe are sown. And when the universe reaches a singularity, an infinitely dense point, it could erupt once again into a new Big Bang. Some models even suggest that information and structure from one cycle could subtly influence the next. Patterns of cosmic microwave background radiation, for example, might carry faint echoes of universes long past. If true, then our universe is not just an isolated moment, but a page in a cosmic book that has been rewritten countless times, each time with variations, yet following a rhythm as old as existence itself. There are multiple versions of the cyclic theory. Some depend on modifications of general relativity. Others rely on the interplay between extra dimensions, such as those proposed in string theory and brain cosmology. One variant involves two parallel universes, brains, that periodically collide, causing a new Big Bang every time they touch. Each universe may live for trillions of years before falling back into a cosmic embrace, birthing new stars, new physics, and perhaps new forms of life. In this view, 1 trillion years from now does not mark an end, but a turning point. It may be the calm before contraction or the silence between heartbeats. The apparent stillness of the far future might be like the brief pause before an orchestra plays again, a moment filled with potential energy waiting to explode back into form and light. Unlike heat death or the Big Rip, which suggest a one-way journey into oblivion, the cyclic model introduces hope. It implies a universe with no ultimate death, only transformation. Life, matter, and structure could continually re-emerge with each cycle, perhaps in new forms, governed by subtly different laws. The cosmos may forget, but it also may remember, in the curvature of space, in quantum fluctuations, or in hidden dimensions beyond our perception. Yet, such a grand cycle raises philosophical and physical questions. Can entropy really reset itself? Would each universe become more disordered than the last? Or does the collapse erase all previous entropy, allowing a clean slate? These remain unresolved, with some theorists arguing that only a perfect balance of forces can make cyclic renewal possible. Others suggest that quantum gravity or unknown physics might intervene, preserving the cycle despite apparent violations of thermodynamics. As we push forward through the eons, the universe in this model would see countless cycles, each trillions of years long. Galaxies may reform in new patterns, stars may ignite anew, and perhaps civilizations will rise again, unaware that they exist in just one loop of an eternal spiral. Every moment, no matter how distant or desolate, could be both an end and a beginning. If the cyclic theory holds true, then our current universe is not special because it is early in time, but because it is one among countless iterations. Its beauty and tragedy lie in its impermanence. Nothing lasts forever, and yet everything may come again. Stars die, but stars return. Space expands, but space may contract. Time moves forward, but history repeats on a scale beyond imagination. In the silence, a trillion years from now, when all light has faded and the universe is poised in shadow, we may not be witnessing a death, but a quiet breath drawn before the next great cosmic exhalation. The end, as it turns out, might be the very first step toward a new beginning. The idea of vacuum decay stems from the understanding that the universe might not be in its most stable configuration. According to quantum field theory, the vacuum we perceive as empty space is actually a sea of fluctuating energy, teetering on the edge of stability. This energy level, while seemingly constant, may not represent the true ground state. Instead, it could be what physicists call a false vacuum, a local minimum in the energy landscape that only appears stable but is actually prone to a catastrophic shift. This false vacuum is like a ball resting in a shallow valley, while a deeper, more stable valley lies just beyond a small hill. If the ball were to quantum tunnel through or be nudged over this hill, it would roll down into the deeper valley, representing a transition to a true vacuum. In this apocalyptic scenario, the implications are staggering. The very fabric of physics would be rewritten. The constants we hold dear, such as the speed of light, the strength of gravity, and the behavior of fundamental particles, could all be altered in an instant. A bubble of this true vacuum could spontaneously form somewhere in the cosmos, perhaps due to quantum fluctuations or some high-energy event. Once initiated, the bubble would expand at the speed of light, consuming everything in its path. There would be no warning, no escape, no signal preceding its arrival. One moment, the universe is as we know it. The next, its entire structure is obliterated and replaced with a new set of physical laws. Now consider this happening a trillion years into the future. By then, the universe will have aged beyond recognition. Galaxies will be separated by incomprehensible distances. Stars will be extinct, black holes mostly evaporated, and matter will be rare and diffuse. Yet in this vacuum decay scenario, age and distance mean nothing. The vacuum bubble will not slow down. It will not be deterred by distance or emptiness. It will sweep through the darkness as an unstoppable cosmic tsunami, instantly annihilating the old universe and replacing it with a new, unknown reality. One of the most chilling aspects of this theory is that it renders the future fundamentally unpredictable. We could calculate the trajectory of stars, the evaporation times of black holes, the slow fade of light across eons. But vacuum decay operates outside that framework. It could happen tomorrow or in a trillion years. The timing is dictated not by the gradual unfolding of entropy, but by the whims of quantum instability. If we were to peer into this future from the safety of a vantage point, watching the universe from some other dimension immune to its laws, we might see this bubble emerge quietly, without flair. Perhaps in a pocket of the farthest reaches of an unlit void, it begins. No light accompanies it, no sound, just a sudden change, unnoticed until it is too late. The bubble grows. It consumes a starless region of space, then engulfs ancient black dwarfs, perhaps even the last dying ember of a civilization that waited too long for a future that would never arrive. In this transformed universe, what comes next is unknowable. If life somehow persisted before the vacuum decay, it would be obliterated. If fundamental particles were restructured, the familiar chemistry of atoms and molecules might become impossible. The laws governing time itself could be reshaped, making causality incoherent. Or perhaps, in some eerie twist, the new vacuum supports a reality just as rich as ours, only alien and inaccessible to any consciousness we could recognize. There's an irony in how vacuum decay might represent both a final death and a new beginning. From the ashes of one universe, another is born, not through rebirth in the traditional sense, but through a radical redefinition of what existence means. In this way, vacuum decay is not merely a threat. It's also a philosophical puzzle. It challenges the notion of permanence and finality. If even the vacuum of space is unstable, then nothing in the cosmos can truly be called eternal. A trillion years from now, the universe may be so quiet, so void of activity, that any shift would be unfathomably noticeable, if there were anyone or anything left to notice. But vacuum decay doesn't require observers. It happens whether there's a witness or not. The universe doesn't seek permission to end. It simply continues along a path of instability until the inevitable collapse occurs. This theory also intertwines with ideas about the multiverse. If vacuum decay is possible in our universe, it could also occur in other pocket universes scattered across an unimaginably vast multiversal landscape. Perhaps somewhere out there, other bubbles have already formed and consumed their own spaces. Perhaps ours is next, or perhaps the stability we enjoy is a fortunate statistical anomaly, and the vast majority of universes fall to decay soon after forming. Another sobering realization is that no action we take could prevent or even anticipate this transformation. No detector could see a bubble coming. No technology could outrun it. Even a trillion years of progress would be rendered meaningless against this silent force of quantum inevitability. It underscores a fundamental humility in the face of cosmic processes. No matter how advanced, how wise, or how prepared a civilization becomes, some fates remain entirely beyond intervention. In the long narrative of the cosmos, vacuum decay is the ultimate wild card. It represents an end not through slow withering or violent explosion, but through a sudden shift so profound it defies our most basic assumptions. 1 trillion years of history, of entropy, of memory, could be erased in less than a heartbeat, and what comes after would bear no resemblance to anything that came before. Whether or not vacuum decay ever occurs, its mere possibility injects a deep uncertainty into the universe's future. As physicists refine their understanding of particle fields and cosmological stability, we may someday learn if the false vacuum is a real threat. Until then, it remains a terrifying footnote in the story of eternity, always lurking, always possible, forever unreadable in the fabric of time. The multiverse renewal theory presents an astonishing perspective on the destiny of our cosmos. one that transcends the idea of a solitary universe winding down in isolation. Instead, it posits that our universe is merely a single bubble within an unimaginably vast multiverse, a foamy expanse filled with countless other universes, each with its own unique physical laws, constants, and histories. These universes, like bubbles in a cosmic ocean, emerge, expand, fade, and collapse independently, yet all contribute to a grander, ongoing process of cosmic renewal and transformation. The notion that our universe might be just one transient bubble challenges our conventional ideas about permanence and uniqueness, inviting us to envision a cosmic ecosystem on a scale so vast that even 1 trillion years seems but a fleeting moment. Within this framework, the lifespan of our universe, its birth, evolution, and eventual decline, is just one phase in a much larger multiversal cycle. As our universe drifts toward its distant future, cooling and darkening, with stars burning out and black holes evaporating, other bubbles may be forming elsewhere in the multiverse, igniting new big bangs and giving birth to fresh realms of space, time, and matter. In 1 trillion years, while our own cosmos might be cold, dark, and virtually lifeless, new universes could be blazing with energetic creation, teeming with the possibility of stars, galaxies, and perhaps life forms alien beyond our wildest imaginations. The multiverse itself can be conceptualized in several ways, each with subtle but profound differences. Some models envision a fractal-like, eternally inflating space, where bubbles continually bud off, each a self-contained universe expanding and evolving under its own laws. Others suggest a cyclic renewal, where universes arise, decay, and collapse in rhythms extending beyond our comprehension. The key takeaway in the multiverse renewal theory is that universes do not simply die out into nothingness. Instead, they contribute to an ongoing cosmic process, where death in one bubble seeds the possibility of birth elsewhere. The implications of this theory for 1 trillion years into the future are staggering. Our own universe, with all its galaxies, planets, and potential for life, will have long passed its prime. But somewhere beyond the limits of our observable horizon, indeed beyond any horizon, new universes will be blooming like celestial flowers in a dark garden. These newborn universes might differ dramatically from ours, with altered physical constants that allow for phenomena and forms of existence utterly foreign to us. This raises profound philosophical and scientific questions. If the multiverse is constantly renewing itself, does that mean that cosmic evolution is infinite? Does the notion of ultimate heat death or big rip lose meaning when balanced against an eternal, infinite multiversal dance of birth and decay? From the perspective of the multiverse, the ultimate end may be no more than a pause in a far grander story, where universes are ephemeral threads in an endless tapestry. At the scale of 1 trillion years, the boundaries of our own universe will be pushed to their limits. Accelerated expansion driven by dark energy will have pushed distant galaxies beyond the cosmic event horizon, making them forever inaccessible to any observer within our bubble. Yet, this isolation within the bubble universe contrasts sharply with the idea that beyond these horizons, other universes may be thriving. The multiverse becomes a grand arena where multiple realms exist independently, their causal boundaries impenetrable to one another, yet linked in the greater fabric of existence. An especially intriguing aspect of the multiverse renewal theory is the possibility of universe recycling. Some speculative ideas suggest that when a universe dies, the information, energy, or structure within it might somehow seed or influence the birth of new universes. This recycling could be a physical process or a more abstract metaphysical one, but it implies a cosmic conservation principle on a scale that dwarfs our current understanding. The ashes of one universe could become the spark of another, ensuring that the totality of existence is never truly lost but continually reborn. Moreover, this theory raises questions about our place within such a vast multiversal landscape. If countless universes exist, each with differing laws and parameters, then the particular conditions that allowed for our existence, our physical constants, the formation of complex atoms, the emergence of life, might be incredibly rare or just one possibility among an infinite set. This reframes the anthropic principle, suggesting that we observe our universe's fine-tuned conditions simply because we exist here, but many other universes might be inhospitable or radically different. From a cosmological observation standpoint, the multiverse remains challenging to prove or disprove. Its very nature places most other universes beyond observational reach, separated by fundamental causal barriers or dimensions inaccessible to our instruments. Nonetheless, theories like eternal inflation and string theory hint at multiverse structures, providing a rich theoretical foundation that bolsters the plausibility of such models. Future advances in quantum gravity or novel observational techniques might someday offer indirect evidence. But for now, the multiverse renewal theory resides largely in the realm of profound and humbling speculation. One striking image is that of our universe as a flickering candle in an immense dark hall filled with countless other candles, some newly lit, some fading, others yet to ignite. The flicker of our candle represents the transient nature of cosmic existence. No matter how long it lasts, it is but a moment in an eternal interplay of light and darkness on a scale that dwarfs human comprehension. Furthermore, the renewal of universes in the multiverse might not be limited to spontaneous creation. There could be intricate processes governing how new universes emerge, perhaps through mechanisms akin to cosmic reproduction or branching, where universes give rise to offspring with slight variations in physical laws akin to evolutionary mutations. This introduces a dynamic multiverse where selection pressures operate on universes themselves, favoring those with properties conducive to longevity or complexity. In this grand multiversal vista, 1 trillion years from now, our universe may be a distant memory, an abandoned shell among many. The stars and galaxies that once dazzled will have vanished into cold darkness, but the cosmic foam continues to churn with the birth of new realities. Each universe's rise and fall might contribute to a greater cosmic balance, ensuring that existence endures, even as individual universes cease to be. The multiverse renewal theory also opens doors to questions about consciousness and existence. If new universes continually form, might life or consciousness arise again, perhaps in forms incomprehensible to us? Are there infinite variations of existence, with infinite versions of reality playing out simultaneously? This vast multiplicity suggests an endless frontier for discovery and wonder, far beyond the confines of our own cosmic bubble. In conclusion, while the distant future of our universe may seem bleak or silent, the multiverse renewal theory offers a vision of hope and continuity on an unimaginable scale. It invites us to see ourselves as part of a vast cosmic ocean, where universes ebb and flow like tides, each a transient moment in the endless rhythm of creation and dissolution. In 1 trillion years, our universe might be but a forgotten bubble, but the multiverse will persist, ever renewing, ever expanding, and forever alive with potential. As we delve into the frozen time hypothesis, the very fabric of reality seems to take on a surreal, almost paradoxical character. Time, which we perceive as an ever-forward flow, a relentless march from past to future, might lose its defining essence as entropy approaches its theoretical maximum. In this view, the arrow of time, the one-way direction in which events unfold, is intimately tied to the increase of entropy, the measure of disorder in a system. As entropy rises relentlessly over trillions of years, the processes that once drove change begin to falter, slow, and finally approach a state where change itself becomes imperceptible. Imagine a universe where the kinetic dance of particles, the flickering of photons, and the swirling of galaxies all come to a near halt, not due to an external force, but because the fundamental thermodynamic gradients that sustain motion and change have all but disappeared. In such a cosmos, the clocks that mark the passage of time, both mechanical and biological, would cease to tick in any meaningful way. Without the contrast between order and disorder to define past and future, the distinction between moments fades away and time effectively freezes. At the 1 trillion year mark, the universe might have reached such a profound state of entropy saturation that it becomes a vast, static tableau. Instead of dynamic evolution, the cosmos would be like a snapshot suspended indefinitely. No events occur, no new structures form or decay, and the flow of cause and effect grinds to a near stop. This frozen state is not simply a pause or sleep. It is a fundamental alteration in the nature of time itself, where the arrow that points forward no longer exists, leaving behind a ghost-like cosmos. From a human perspective, this concept challenges our deepest intuitions about time and change. Our entire experience, our memories, our sense of self, depend on the progression of moments. Without change, without the passage of time, the universe becomes a still image without a story to tell. The implications for consciousness and existence in such a frozen cosmos are profound. Life, as we know it, requires time to unfold, to process information, and to evolve. Without time's arrow, life would be impossible, and the universe would enter a realm beyond life, beyond death, beyond becoming. Physically, the slowing of processes would stem from the thermodynamic equilibrium reached at maximal entropy. Energy gradients that power reactions, motion, and transformations vanish. Photons would lose their energy to redshift caused by cosmic expansion, eventually becoming so low energy they no longer interact effectively with matter. Atomic and subatomic transitions, which underpin the very fabric of physical phenomena, would slow drastically or stop. In this scenario, the universe exists in a near-perfect balance where no change occurs. Quantum mechanically, even the probabilistic fluctuations that punctuate the vacuum might diminish in their effect or become irrelevant at this scale. The usual passage of time, as encoded in the Schrödinger equation, might lose operational meaning in a frozen temporal landscape. This suggests that time itself might be an emergent property dependent on non-equilibrium states. Without gradients or asymmetries, time's flow could vanish. Cosmologists considering the frozen time hypothesis often discuss it as a limiting case of the heat death scenario, where not only does temperature approach absolute zero, but temporal dynamics also approach a standstill. The universe's history becomes a closed book, eternally unread and unchanging. This timeless cosmos challenges the fundamental assumptions of physics that rely on change and evolution to describe reality. Moreover, the concept raises metaphysical questions about the nature of existence without time. If nothing changes and moments do not succeed one another, can existence be said to persist? Is a timeless universe equivalent to a non-existent one? Or is it a unique mode of being utterly alien to our experience, yet real in its own right? These questions push the boundaries of philosophy, physics, and cosmology. At the scale of 1 trillion years, the frozen time hypothesis implies that the cosmos transitions from a dynamic system to a static one. Galaxies no longer merge or drift apart. Black holes cease their slow evaporation, and the cosmic microwave background radiation settles into a uniform, cold glow. Matter may remain arranged in some configuration, but without time's passage, these configurations never change or evolve. The universe becomes a perfect still life, a frozen sculpture of matter and energy. In such a state, conventional notions of causality break down. Cause and effect depend on temporal succession. Without time's arrow, causes and effects lose their order and meaning. This might render the universe fundamentally incomprehensible from any internal perspective. Observers, if any could exist in such conditions, would be unable to perceive change, making observation and measurement impossible. Interestingly, this hypothesis also suggests a limit to how far entropy-driven decay can push the universe. Rather than devolving into chaos or disorder, the universe settles into a kind of ultimate stasis, a final equilibrium where change is frozen and the flow of time is arrested. This static state could persist indefinitely, as there would be no internal mechanism to restart motion or change. Philosophically, the frozen time hypothesis invites us to reconsider the significance of time as a dimension. Unlike space, which can be mapped and explored without necessarily implying change, time in our experience is inseparable from motion and events. If time can freeze, does that imply time is not fundamental but emergent? Could it be a byproduct of thermodynamic gradients rather than a basic feature of the universe? This idea aligns with some modern approaches in theoretical physics, where time emerges from entanglement and quantum correlations. In these views, the degradation or disappearance of such correlations at extreme entropy might erase time itself. Thus, the frozen time hypothesis may find footing in future quantum gravity theories or cosmological models yet to be developed. Practically speaking, while 1 trillion years is unimaginably long by human standards, it is still a near future cosmologically in this scenario, marking the universe's entry into this ghostly, frozen state. Beyond this epoch, no significant events occur. The universe is an eternal stillness where the future is indistinguishable from the past. In the grand cosmic narrative, the frozen time hypothesis paints a picture of ultimate stillness. No fireworks, no drama, no evolution. Just the quiet, eternal pause of everything that once was. It is a vision both haunting and awe-inspiring, reminding us how deeply our experience of existence is tied to the flow of time and how fragile that flow might ultimately be. To imagine a universe where time has frozen is to confront the ultimate cosmic silence, a timeless void that challenges every notion of change, existence, and reality itself. In 1 trillion years, if the frozen time hypothesis holds true, the universe would become a spectral monument to a past that no longer unfolds, an infinite present without motion or becoming. The entropy reversal hypothesis offers an intriguing and somewhat hopeful counterpoint to the prevailing notion that the universe's future is a one-way journey toward disorder and decay. While the second law of thermodynamics asserts that entropy, the measure of disorder or randomness, tends to increase over time in a closed system, this hypothesis suggests that under certain rare quantum conditions, entropy could spontaneously reverse, either locally or even on a cosmological scale. Imagine, after 1 trillion years of relentless decay, where the universe is largely cold, dark, and desolate, a sudden and profound quantum fluctuation occurs. This fluctuation, seemingly improbable by classical standards, might produce a new region where entropy flows backward instead of forward. In this low-entropy pocket, matter and energy could spontaneously organize into more ordered structures, effectively igniting a rebirth or a fresh cycle of cosmic evolution. This concept stretches our understanding of thermodynamics by introducing the possibility that entropy is not an absolutely irreversible process, but one that, in rare circumstances, could flip direction. While everyday experience and conventional physics strongly favor entropy increase, quantum mechanics often allows for outcomes that seem forbidden or highly unlikely in classical terms. The entropy reversal hypothesis taps into these peculiar quantum probabilities, where the very fabric of space-time might suddenly experience a spontaneous ordering event. From a cosmological perspective, this reversal could mark the birth of a new baby universe within the vast expanse of the old one. Instead of the familiar Big Bang beginning the universe anew, this new low-entropy region might expand and evolve, possibly independent from its parent cosmos. It could reset physical laws locally, allowing stars, galaxies, and eventually life to arise once more in an entirely fresh environment. If such reversals are possible, the universe may not be fated to end in eternal heat death or cold darkness, but instead could undergo cycles of decay and renewal. Each reversal would act like a cosmic reset button, bringing about a rejuvenation of order and complexity from the ashes of entropy's climb. These cycles might not be periodic or predictable, but spontaneous and scattered across vast temporal and spatial scales. At the 1 trillion year mark, the entropy reversal hypothesis introduces a tantalizing possibility. The universe might still harbor the seeds of its own regeneration. While the majority of space has become a graveyard of entropy, quantum fluctuations at a fundamental level could defy the universal trend, sparking pockets where time's arrow bends backward and disorder resolves into order. Such a process might unfold as a localized bubble or island of low entropy, where physical laws reshape and new particles and forces emerge. The surrounding high-entropy environment might seem frozen in decay, but within this bubble, thermodynamic processes restart, setting the stage for complexity, structure formation, and potentially even life. This picture resonates with some interpretations of the multiverse or cyclic universe models, where universes continually emerge, evolve, and perish. The entropy reversal hypothesis, however, emphasizes that these new beginnings could originate from quantum mechanical processes intrinsic to our own universe's late stages, not necessarily requiring external influences or collisions with other universes. On a more theoretical level, this hypothesis challenges the absoluteness of the second law of thermodynamics on cosmological scales, suggesting it may be a statistical tendency rather than an inviolable law. Just as rare events like spontaneous drops in entropy can happen locally in small systems, perhaps cosmic scale reversals can emerge over incomprehensibly long timescales. The implications for cosmology are profound. If entropy reversal occurs, the universe's end might not be a final terminus, but a passage to something new, an eternal cycle of death and rebirth akin to natural cycles observed in biological and ecological systems, but on an unimaginable cosmic scale. Physicists pondering the entropy reversal event often speculate on its triggers. Quantum tunneling, vacuum fluctuations, or unknown interactions within the dark sector of the universe might catalyze this reversal. Some propose that unknown physics beyond the Standard Model could provide mechanisms for such profound changes in entropy flow. From a philosophical standpoint, the entropy reversal hypothesis offers a cosmic optimism, the possibility that the universe contains within itself the means of regeneration and rebirth. It suggests a cosmos not locked in a permanent slide into cold death, but capable of spontaneous renewal, forever cycling between order and disorder, creation and destruction. If true, the trillion-year future is not a barren wasteland, but a cosmic waiting room for the next act. The vast silence of a decayed universe could suddenly break with the birth cry of a new low-entropy bubble, signaling the dawn of a new cosmos where complexity and life might arise once more. In practical terms, detecting or proving this hypothesis is profoundly challenging. The timescales involve dwarf human history and even the entire lifetime of stars and galaxies. Yet, theoretical models continue to explore conditions under which entropy might reverse, linking quantum mechanics, cosmology, and thermodynamics in unprecedented ways. For observers still able to perceive or measure the universe at these epochs, if such observers could exist, the emergence of a low-entropy region would appear as a profound anomaly, a bright spot of order in an otherwise decayed universe. This newborn pocket could represent a beacon of hope in an otherwise bleak cosmic landscape. In summary, the entropy reversal hypothesis posits that the universe might defy its ultimate fate by spontaneously generating new low-entropy regions from quantum events. After a trillion years marked by decay and increasing disorder, this quantum twist could spark the birth of an entirely fresh cosmic cycle, a new beginning born from the heart of cosmic entropy's apparent end. Information preservation theory explores one of the most profound puzzles in modern physics: the fate of information as the universe approaches its most distant future stages. While the material components of the cosmos, stars, planets, and even atoms, may degrade, break down, or evaporate, this theory proposes that the fundamental information that defines the universe's history never truly vanishes. Instead, it is conserved in subtle and complex ways, encoded into the positions, quantum states, and correlations of the remaining particles. As we look forward to a universe aged 1 trillion years, matter, as we understand it, will have undergone immense transformations. Stars will have long since burned out, galaxies will have dispersed, and black holes may be evaporating through Hawking radiation. Yet, despite this apparent desolation, the quantum fabric of space-time may preserve an intricate record of everything that ever occurred. Information preservation theory posits that the universe essentially becomes a vast, silent crypt where the echoes of all events, past, present, and future, are encoded at the deepest level. This idea finds its roots in the fundamental principle of quantum mechanics that information cannot be destroyed even as physical systems undergo radical changes. In particular, black hole physics has fueled debates about whether information swallowed by black holes is lost forever or somehow encoded on their event horizons. This so-called black hole information paradox challenged classical physics, but many modern theories suggest that information escapes or remains imprinted, perhaps through Hawking radiation or holographic principles. Extending this concept cosmologically, the information preservation theory suggests that as ordinary matter decays, protons disintegrate, atoms fall apart. The underlying information carried by these particles does not disappear. Instead, it becomes encoded within the quantum states of residual particles, radiation, or the subtle structures of space-time itself. This could mean that, a trillion years from now, what remains of the universe is not a blank void, but an almost frozen tapestry holding an unbroken narrative of cosmic history. In such a far future universe, observers, if they exist or arise, would find themselves in a reality where physical matter is sparse and scattered, yet every bit of information about the universe's prior existence is encrypted within quantum states, entanglements, or patterns in the cosmic background. The universe transforms into an unreadable but complete record, an archive so vast and delicate that comprehending or decoding it would require technologies and cognitive abilities far beyond present human understanding. This theory challenges the traditional notion of cosmic ending as an erasure. Instead of a final silence where nothing remains, it paints a vision of enduring legacy. The essence of every star formed, every particle collided, and every life lived could be preserved eternally in a form imperceptible but intact. The cosmos, though seemingly empty, is a repository of eternal memory. The notion also resonates with ideas from the holographic principle, which suggests that all the information contained in a volume of space can be represented on a boundary surface. This principle offers a mathematical framework for how information can be stored in ways that defy ordinary three-dimensional intuitions. In a trillion years, the universe might look like a near-empty volume, but be encoded holographically with its entire history. From an information theoretic perspective, this implies that the physical dissolution of matter and energy does not equate to the loss of knowledge or data. Information preservation means that fundamental quantum correlations and entanglements survive the decay of conventional structures. This could transform our understanding of the universe's fate from one of oblivion to one of lasting memory. Philosophically, the information preservation theory touches on profound questions about the meaning of existence and memory on cosmic scales. If information persists eternally, then in some abstract sense, nothing is ever truly lost. The universe itself becomes a vast, immortal ledger where every event, no matter how fleeting, is conserved at the quantum level. On a practical level, how this information might be accessed or interpreted is an open question. The universe's extreme age and entropic state would mean that any signal or data is deeply encoded in noisy, low-energy particles or diffuse radiation. Detecting these faint quantum imprints will be nearly impossible for any known form of life or technology. Yet, the principle stands that the blueprint of all cosmic history remains present. Furthermore, this theory aligns with ideas from quantum gravity and string theory, which strive to reconcile gravity with quantum mechanics and provide a complete description of the universe. In these frameworks, space-time itself may have a quantum informational structure, suggesting that the fabric of reality is fundamentally about information. In the context of a trillion-year future, this means that even as black holes evaporate and protons decay, the universe's informational essence might survive encoded in quantum fields or exotic particles. The universe becomes a timeless monument to its own past, a silent crypt containing the sum of all that has ever transpired. Information preservation theory also invites speculation about the ultimate fate of consciousness or memory on cosmic scales. If information is never lost, could some aspect of consciousness or identity as patterns of information persist in the far future? Although speculative, this possibility intrigues physicists and philosophers alike. This enduring information might be considered a cosmic record, waiting for an advanced intelligence or a future civilization capable of deciphering the universe's complete history. The vastness and complexity of this record would challenge comprehension, but also offer an unparalleled opportunity to understand the cosmos and ourselves. At 1 trillion years, then, the universe might appear as a cold, dark expanse, but internally remain a rich repository of encoded information, a timeless archive preserving the cosmic narrative indefinitely. This stands as a profound testament to the power of information as a fundamental constituent of reality. In conclusion, the information preservation theory redefines cosmic death not as oblivion, but as transformation. Matter may decay, stars may fade, and space may stretch infinitely, but the universe's informational legacy is immortal. It waits silently in the far future, a cryptic testament to existence itself, encoded in the subtle quantum dance of particles and fields. Simulation decay theory ventures into a fascinating and deeply speculative realm of thought. The possibility that our entire universe is a sophisticated simulation, an artificial construct created by some advanced intelligence or civilization. If this hypothesis holds any truth, the far future of the universe, 1 trillion years from now, might not be governed solely by natural laws and physical processes, but also by the integrity, maintenance, and lifespan of the underlying simulation framework. Over such colossal timescales, this artificial cosmos could experience degradation, glitches, or even a complete shutdown, resulting in what we might term the decay of the simulation. This concept arises from the convergence of several modern scientific and philosophical ideas. The rapid advancement of technology suggests that future civilizations might develop the capacity to simulate entire universes indistinguishable from reality itself. If such simulations are possible, and even likely, then the reality we perceive could be one among potentially countless others, all run on some form of computational substrate. This leads to the notion that our universe may not be fundamentally continuous or infinite in its operation, but is subject to the constraints and potential failures inherent to any complex computational system. Projecting forward to 1 trillion years, the simulation that underpins our reality might face multiple forms of deterioration. The first form of decay could be technical glitches, errors in the code, or corruption of the data structures that define the laws of physics and the behavior of particles. These glitches could manifest as anomalous phenomena, inexplicable inconsistencies in physical constants, or abrupt failures of the natural order that scientists and observers would struggle to understand. Over time, these irregularities could accumulate, disrupting the smooth operation of the universe and leading to increasingly unpredictable or chaotic outcomes. Another form of simulation decay could be computational resource exhaustion. Even the most advanced civilizations and technologies might have finite processing power or energy to sustain the simulation indefinitely. Over trillions of years, the burden of running a complex, high-resolution universe might become unsustainable, leading to simplifications in the simulation's detail or eventual cessation. This progressive degradation could cause the universe to appear less detailed, with physics becoming fuzzier, events becoming less precise, or entire regions of space-time becoming unrendered, effectively fading into nothingness. Alternatively, the simulation might be deliberately programmed with a finite runtime. Just as human-made software often has shutdown routines or expiration dates, the creators of our universe simulation could have designed it to end at some point. 1 trillion years might fall within this programmed endpoint, where the simulation is scheduled to stop, reboot, or transition into a different phase or mode. The shutdown could be abrupt or gradual, but the consequence would be the erasure or transformation of the reality we know. The idea of simulation decay also raises profound philosophical and existential questions. If reality itself is artificial, then concepts such as end or death take on new meaning. The universe's fate is no longer solely a physical inevitability, but a function of decisions, maintenance, or errors by an external programmer or system administrator. This reframes the cosmic narrative from one of natural progression to one intertwined with artificial control and potentially even purpose or design. From the perspective of observers within the simulation, the signs of decay might be subtle at first. Anomalies in physical laws, strange breakdowns in causality, or inexplicable disruptions in quantum behavior. Over vast timescales, these would escalate, and the universe might become increasingly surreal or unstable. Eventually, entire regions of space might vanish, or the fundamental constants could shift erratically, leading to a reality unrecognizable from the one that existed billions or millions of years earlier. One intriguing consequence of this theory is the potential emergence of simulation artifacts, unexpected glitches that do not correspond to any known physical process, but rather to computational errors or remnants of debugging code. Such phenomena might include sudden disappearances of matter, spontaneous fluctuations in space-time geometry, or bizarre violations of energy conservation. These signs could mark the slow unraveling of the simulation as it approaches its expiration. The simulation decay theory also suggests a form of cosmic entropy on an informational or computational level. Just as thermodynamic entropy describes the gradual increase of disorder in physical systems, simulation decay represents the increasing corruption or degradation of the underlying code. This computational entropy leads to progressive disorder in the simulation's operation, culminating in a breakdown of the simulated universe. Moreover, if the simulation framework is hierarchical or nested, where our universe simulation is itself contained within a larger metasimulation, then decay could propagate upward or downward through these layers. Problems in the higher-level system could cause cascading failures in our universe, or conversely, the degradation here could be a symptom of instability in the broader computational reality. Considering the immense timescale of 1 trillion years, it's plausible that any artificial simulation would face significant challenges to maintain fidelity, continuity, and coherence. Physical hardware, or whatever substrate supports the simulation, might itself degrade, or the creators might cease maintenance or lose interest. The universe's end, in this case, is not a natural cosmic event, but a technological one, a shutdown of the grandest scale imaginable. Interestingly, this perspective aligns with some interpretations of the Fermi paradox and the search for extraterrestrial intelligence. If many advanced civilizations run simulations, then our universe might be one of many, each with its own life cycle. The end of our universe simulation might coincide with the end of a particular experiment or virtual environment created by an unknown intelligence. Ultimately, the simulation decay theory challenges traditional cosmological endings by introducing an artificial, non-physical layer that controls or influences the universe's lifespan. It expands the scope of cosmic fate beyond physics into realms of information technology, artificial intelligence, and metaphysics. 1 trillion years hence, under this theory, The universe could face a gradual collapse of its operational framework, fading from a coherent cosmos into a fragmented, glitch-ridden shadow of its former self before ceasing entirely. Or it might transition into a reboot or a new simulated phase, hinting at cycles of virtual rebirth. While speculative, simulation decay theory offers a unique lens on the ultimate destiny of reality, suggesting that the cosmos may not just end with heat death or a big rip, but rather with the flicker and fade of a cosmic computer program reaching its final cycle. Dark matter collapse theory explores one of the most enigmatic and least understood components of our universe, dark matter. Comprising approximately 27% of the total cosmic mass energy budget, dark matter does not emit, absorb, or reflect light, making it invisible to current electromagnetic observations. Its presence is inferred primarily through gravitational effects on visible matter, radiation, and the large-scale structure of the cosmos. Despite its invisibility, dark matter plays a critical role in the formation and evolution of galaxies, galaxy clusters, and the cosmic web. Yet, as the universe ages, especially by the unimaginably distant milestone of 1 trillion years, the behavior and fate of dark matter may diverge dramatically from the familiar narrative shaped by baryonic matter. At present, the exact nature of dark matter remains elusive, with numerous hypotheses ranging from weakly interacting massive particles, WIMPs, axions, sterile neutrinos, to more exotic candidates. Its interaction with itself and ordinary matter is incredibly weak or non-existent, which grants it a certain longevity and stability over cosmic timescales. However, theorists have postulated that dark matter could undergo transformations or dynamic evolutions far beyond our current observational window. Over the course of 1 trillion years, these processes might profoundly alter the universe's large-scale architecture in ways we can only begin to imagine. One possible avenue is that dark matter, despite its current apparent stability, could eventually clump together due to its own gravitational attraction into denser, more exotic structures, sometimes referred to as dark matter halos, or even more compact formations analogous to stars or black holes, but composed entirely of dark matter. These hypothetical objects could be fundamentally different from anything in the visible universe, possibly forming dark stars or dark matter condensates held together by gravity or unknown quantum forces. Unlike baryonic stars, these would not shine or emit radiation, existing as cold, dense, and mysterious objects permeating the cosmos. As time stretches toward the trillion-year mark, these dark matter clumps might grow by accreting more dark matter particles, merging with each other, or even capturing residual baryonic matter. The gravitational landscape of the universe would shift accordingly, with large portions of space dominated by invisible dark matter structures exerting enormous gravitational influence on what little visible matter remains. This could lead to a universe where galaxies, stars, and planets are merely sparse islands in a vast ocean ruled by dark matter's complex web. Furthermore, dark matter particles themselves might not be perfectly stable. Some theories predict that dark matter could decay into lighter particles or other forms of unknown exotic matter over timescales vastly exceeding the current age of the universe. This decay could be a slow trickle or an eventual cascade, gradually reducing the dark matter density and altering gravitational interactions on cosmic scales. Such decay products might be highly energetic or interact differently with the fabric of space-time, potentially triggering new cosmic phenomena. Should dark matter begin to decay or rearrange significantly, the cosmic balance maintained over billions of years could be disrupted, leading to profound structural changes. Gravitational wells that once held galaxies and clusters intact could weaken or vanish. Large-scale cosmic filaments composed of dark matter might dissipate or transform, eroding the scaffolding that gives the universe its large-scale texture. Additionally, these exotic dark matter transformations could influence the fate of other cosmic components. For instance, as dark matter collapses or decays, it might alter the behavior of dark energy, the mysterious force driving the accelerated expansion of the universe. The interplay between dark matter and dark energy remains a frontier in cosmology, and changes in one could provoke unexpected responses in the other. At the trillion-year timescale, the cosmic acceleration could slow, halt, or even reverse due to these evolving dynamics, reshaping the ultimate destiny of the cosmos. The presence of dark matter structures could also affect black holes and remnants of ordinary matter in the distant future. If dark matter clumps are sufficiently massive and compact, their gravitational influence might cause the capture or disruption of nearby black holes, potentially forming hybrid objects or exotic states of matter that defy current understanding. Such interactions would transform the dark era of the universe into a far more complex and dynamic epoch, contrary to earlier predictions of quiet emptiness. Dark matter collapse theory invites us to rethink the universe not as a simple fading ember scenario, but as a domain of ongoing transformation driven by invisible, powerful forces. The universe in 1 trillion years, under this model, is no mere silent void but a cosmos where dark matter continues to sculpt, collapse, and perhaps decay, setting the stage for new cosmic phenomena long after the last stars have vanished. In this vision, the vast cold darkness filling the universe is punctuated by immense, hidden dark matter structures whose gravitational pull subtly warps space and time. The familiar cosmic web may fade, but a new dark web dominated by exotic dark matter objects might emerge, unseen but no less real. The large-scale structure of the universe becomes a realm governed by shadowy forces, with gravitational interactions creating a silent dance of invisible giants across the empty void. The changes wrought by dark matter's evolution could also impact the observable effects of gravitational lensing, subtly bending light from the few remaining luminous sources or background radiation. This gravitational lensing dominance might become more pronounced as dark matter clumps grow, bending and distorting the sparse photons traveling through the cosmos. The faint glow of distant remnants might twist and shimmer as it passes through these massive dark matter concentrations, creating eerie and ephemeral cosmic illusions. If dark matter undergoes significant decay, it might also release energy or particles that influence the temperature and energy distribution of the universe's remnants. This could partially counterbalance the cooling trends predicted by other theories like the Big Freeze, introducing localized pockets of energy that prevent complete thermal equilibrium. Such regions could briefly sustain exotic physical processes or even the formation of entirely new kinds of matter and radiation. Dark matter collapse theory also intersects with the question of the universe's ultimate fate. The intricate and poorly understood dynamics of dark matter might mean that our universe does not end in a uniform state of decay or emptiness, but in a heterogeneous landscape shaped by competing processes of collapse, decay, and energy transformation. This adds a profound layer of complexity to cosmic evolution, challenging simplistic visions of the universe's final moments. Moreover, these processes could influence any hypothetical forms of life or intelligence that might persist or arise in the distant future. If some form of advanced life or post-biological consciousness exists or evolves within dark matter structures or in their gravitational influence, the nature of existence at the trillion-year mark could be fundamentally different from anything conceivable today. The universe might transform into a realm dominated not by shining stars or planets, but by intricate, hidden networks of dark matter and energy. In summary, dark matter collapse theory paints a picture of the universe at 1 trillion years as a place of profound mystery and transformation. It moves beyond a familiar narrative of fading light and star death, envisioning a cosmos where dark matter itself becomes the architect of the final cosmic epochs. Whether through clumping, decay, or interaction with dark energy, dark matter's evolution could reshape the cosmos on grand scales, leaving behind a shadow universe rich with hidden structure and untold complexity. This vision underscores how little we truly understand about the universe's deep future and how much remains to be discovered about the fundamental forces shaping cosmic destiny. In 1 trillion years, the universe might be dominated not by the stars we see, but by the invisible, enigmatic matter that has quietly shaped the cosmos since its earliest moments, still active, still evolving, and still shaping the fate of everything we know. Gravitational lensing-dominated universe envisions a far future cosmos where traditional sources of light, stars, galaxies, nebulae, have long since disappeared or dimmed beyond detection, leaving a nearly pitch-black universe. In this epoch, the only clues about the large-scale structure and the presence of matter come from the bending and distortion of faint light passing near massive objects. Gravity, the most enduring force, continues to shape the fabric of space-time, creating subtle but detectable warps that act like cosmic magnifying glasses. These warps allow observers, or perhaps future intelligences, to perceive an otherwise invisible universe by tracing the paths of photons traveling through deep space. As luminous objects vanish, the remaining photons traveling through the cosmos are mostly relics of the past. Low-energy background radiation, scattered light from ancient events, or particles emitted from rare astrophysical processes. Though extremely faint, these photons still traverse the cosmos and interact with massive concentrations of matter, both visible and dark. The gravitational fields of massive remnants, such as black holes, neutron stars, or dense dark matter clumps bend their trajectories, creating characteristic distortions in multiple images known as gravitational lensing effects. This bending of light reveals the presence and distribution of mass, even when the matter itself cannot be seen. In such a universe, the observable cosmos becomes less a collection of shining objects and more a tapestry woven from distortions in light patterns. The sky might appear dark and empty to direct observation, but sensitive instruments, if any exist, could detect the bending of light from distant or background sources, allowing the reconstruction of mass distributions across vast scales. These distortions would act as ghostly imprints of a universe's structure, preserving information about the location, mass, and shape of celestial remnants and invisible matter. The nature of gravitational lensing in this far-future era could be highly complex. Multiple lensing events might overlap as photons pass through a labyrinth of gravitational wells. The resulting patterns might resemble intricate, shifting mosaics of light, hinting at the hidden scaffolding of the universe. This creates an environment where information is not carried by emitted light, but by the subtle geometrical shifts imposed on photons, transforming lensing into the primary means of cosmic observation. Because lensing depends on mass rather than emitted light, it can reveal structures composed entirely of dark matter or black holes. These objects, invisible by electromagnetic means, become detectable through their gravitational fingerprints. Over time, as more traditional matter decays or evaporates, gravitational lensing could reveal an increasingly dark universe dominated by invisible mass clumps whose presence is inferred only through the bending of background photons. The disappearance of active light sources means that the universe loses much of its color and texture. Instead, gravitational lensing transforms the cosmic view into an abstract interplay of shapes and brightness variations. The universe becomes a shadow play of mass-induced light distortion, where the shape and strength of gravitational wells can be mapped, but their precise composition remains uncertain. The information encoded in these gravitational lensing patterns might serve as the last archive of a universe's history. By analyzing the distortions, it may be possible to reconstruct the locations of extinct galaxies, the remnants of ancient star clusters, and even the distribution of dark matter halos. This kind of gravitational archaeology could provide profound insights into the cosmos's past, even when direct observation is impossible. In this epoch, any surviving observers or future civilizations, if they exist, would require extraordinarily advanced technology to detect and interpret these faint lensing signals. Their understanding of the universe would rely not on bright beacons of light, but on the subtle warping of space-time itself, demanding new methods of data collection and analysis grounded in gravitational physics. Furthermore, the dominance of gravitational lensing as the main observable phenomenon highlights the persistence of gravity as a fundamental force in the cosmos. While electromagnetic signals fade, gravity continues its quiet influence, structuring the universe on all scales and providing a faint but persistent cosmic fingerprint. The interplay of gravity and light in this scenario also raises fascinating philosophical and physical questions about perception and reality. If all direct sources of illumination vanish, but gravitational lensing preserves the shape of the cosmos, is the universe still visible in any meaningful sense? This epoch could redefine what it means to observe or understand the cosmos. The gravitational lensing-dominated universe could also be affected by the gradual evaporation of black holes via Hawking radiation. As these massive lenses shrink and disappear, the strength and frequency of lensing events would decrease. Eventually, the universe might reach a state where even these gravitational imprints become too weak to detect, plunging all knowledge of cosmic structure into obscurity. The long-term fate of such a universe might be a silent, dark expanse where the last remnants of matter, black holes and dark matter clumps, have slowly faded or evaporated. The final photons traversing this vast emptiness carry the imprint of past mass distributions, but the sources of those imprints become unreachable or non-existent. From a cosmological perspective, gravitational lensing-dominated epochs highlight the resilience of information encoded in the geometry of space-time. Even as conventional energy sources vanish and entropy maximizes, gravity's influence persists, providing a kind of cosmic memory written in the bending of light paths. The universe at this stage may appear static or frozen to casual observation, but the complex gravitational interactions underlying lensing patterns could still reveal dynamic processes, merging black holes, shifting dark matter halos, or residual gravitational waves, illuminating a cosmos in slow but persistent motion. Ultimately, the gravitational lensing-dominated universe underscores the profound connection between matter, energy, space, and time. Even as the cosmos approaches ultimate entropy and darkness, the geometry of space-time preserves a ghostly trace of its structure, allowing for a faint, spectral vision of the universe that once was. This vision challenges us to expand our conception of observation, suggesting that light need not be emitted to be detected, and that the universe's story can be read from the shadows it casts upon itself. As the trillion-year mark approaches, gravitational lensing may represent the universe's last window into its vast and mysterious expanse, a silent testament to the power of gravity and the persistence of cosmic structure beyond all visible light. In the framework of the ultra-slow expansion theory, the universe doesn't collapse or accelerate into a chaotic end. Instead, it simply continues to expand forever, but at an ever-decreasing rate. Initially, this deceleration might go unnoticed, dwarfed by the earlier, faster phases of cosmic growth. But over trillions of years, this slowing becomes the defining rhythm of existence. No dramatic endings, no violent conclusions, just the quiet, unending stretch of space itself into deeper and deeper emptiness. At the trillion-year mark, expansion persists, but at a pace so subtle, so glacial, that it verges on stillness. Yet even this slow drift reshapes the destiny of the cosmos. As expansion stretches space further, galaxies continue to recede from one another, but the rate at which this occurs becomes vanishingly small. The universe thins out like a drop of ink in an ever-deepening ocean. Matter, once densely packed into stars and galaxies, is now so dispersed that vast volumes of space contain only a whisper of atoms. This dilution doesn't destroy matter, but it renders its organization and cohesion nearly impossible. Structures like stars, planets, and even atoms become rarer until they're virtually non-existent. The near standstill of cosmic expansion doesn't equate to stability. Rather, It leads to a kind of existential suspension, a phase in which change happens at a pace too slow for any conceivable observer to detect. Processes that once occurred over seconds or years now take place over eons, and the timelines for change become absurdly long. Entropy increases, but so gradually that it appears to freeze. The universe becomes a silent ballet of potential rather than kinetic motion. This deceleration in cosmic growth also means that the background radiation, already stretched into long radio waves, becomes even more diffuse. Photons that once bounced energetically across the universe now languish in cold, slow waves, undetectable by any current technology. The night sky, once ablaze with stars and galaxies, would now be a uniform void, not because the light has died, but because it has slipped so far across the spectrum that it no longer interacts meaningfully with anything. In this environment, time itself loses clarity, without events to punctuate it. No supernovae, no galaxy mergers, no starbirths. Time becomes an abstract measure, an endless horizon that lacks distinct markers. The arrow of time, always tied to change, begins to blur. The distinction between past, present, and future thins, and the universe feels increasingly timeless even though it is still moving forward. The ultra-slow expansion theory may also predict the survival of certain exotic remnants. Neutrinos, stable elementary particles, and hypothetical dark matter particles may persist. However, they exist in such sparse concentrations that interactions become cosmically rare. A single interaction could take longer than the current age of the universe. These particles drift aimlessly, scattered across unfathomable expanses of space, disconnected from each other in any practical sense. Black holes, depending on their size, may still linger, although many will have evaporated via Hawking radiation long before the trillion-year milestone. Those that remain may be stretched so far apart that each one becomes the only object within its observable universe. In this way, the ultra-slow expansion doesn't just isolate galaxies. It isolates every object, every particle, making interaction nearly impossible and the universe effectively silent. With expansion creeping onward, the curvature of space may also trend toward flatness. Already considered nearly flat by current measurements, space could reach an extreme version of flat geometry in this future, an environment where geometry has no meaningful variance and the vastness of space stretches in perfect uniformity. Distances lose their sense of scale when nothing moves, nothing changes, and all directions are the same. Paradoxically, the universe remains infinite in volume even as it empties of content. This boundless void is not static. It is still governed by the slow pulse of expansion, but the pace is so minimal that infinity itself seems to pause. The result is a kind of cosmic limbo, an eternal twilight of motion that never fully stops, but never significantly progresses either. In such a scenario, if consciousness or artificial intelligence were somehow preserved, they would experience the cosmos as an almost perfectly static backdrop. To perceive change would require lifespans of inconceivable duration. Memory, computation, and awareness would have to function over time frames that defy our understanding of persistence. Without input or variation, thought itself might fade into stillness. The ultra-slow expansion theory offers a haunting vision of eternity, not a fiery end, not a collapse into singularity, but an endless continuation into thinness and stasis. Here, the universe does not die. It just becomes less alive with every passing epoch. No catastrophe marks its conclusion. No event defines its finale. Instead, it persists, and in that persistence lies a new kind of cosmic finality. Not the end of time, but the end of meaningful change. Even in this stillness, however, laws of physics continue to operate, albeit in the background. Quantum fluctuations may still occur, but the probability of them having any significant effect is infinitesimal. The universe enters a mode where the potential for events exists, but the energy density and spatial connectivity required to realize them simply isn't there. This vision challenges not just our understanding of the universe's fate, but our definition of existence. Can something that changes so slowly it seems motionless still be called alive? Does expansion without activity still constitute time? These are not just scientific questions, they're philosophical ones, pointing to the outer limits of meaning itself. Ultimately, the ultra-slow expansion theory posits that the universe, in its oldest age, might not explode, collapse, or freeze, but instead dissolve, not in temperature or matter, but in complexity, in interaction, in significance. A slow dissolution into an eternal stretch of space too empty to care and too quiet to notice. In the distant epochs beyond stars, galaxies, and even particles, the universe may regress to its most primal state, a churning, chaotic substrate known as quantum foam. This concept, proposed in the framework of quantum gravity, envisions space-time not as a smooth continuum, but as an unpredictable froth at the smallest scales. As time stretches to 1 trillion years and beyond, and all ordered structure evaporates or decays, quantum foam could become the dominant feature of reality. It would be a universe stripped bare, not to emptiness, but to pure uncertainty. This foam isn't made of matter or energy in the traditional sense. Instead, it is the seething, fluctuating nature of space-time itself at the Planck scale, so tiny that 1 trillion of these units barely span an atom. Here, dimensions blur, causality wavers, and the smooth geometry of the cosmos breaks down. If every particle has decayed, every black hole evaporated, and all fields flattened, then the universe may become a sea of these unpredictable microstructures, writhing, collapsing, reforming with no pattern and no permanence. Even time may not behave as we expect in a quantum foam-dominated universe. At this level, the usual progression from past to future may lose coherence. Instead of a flowing arrow of time, there might be flickers of potential realities, short-lived and probabilistic, bubbling into and out of existence. Each moment could spawn an infinite variety of possible outcomes, none stable enough to cohere into lasting events, but all part of the fundamental jitter of space-time itself. The large-scale order that once defined galaxies, solar systems, and atoms would be gone. There'd be no constants, no horizons, no matter, just fluctuations governed by quantum principles. These fluctuations, unlike thermal noise or background radiation, are not remnants of past events. They're the default state of reality when all else is stripped away. 1 trillion years into the future, the universe might not be a cooling graveyard, but an eternal froth of indeterminacy. Some theories suggest that this foam could be the birthplace of new realities. Random spikes in energy might give rise to new space-time regions, perhaps budding off as baby universes separate from our own. These bubbles could inflate into new cosmoses, each with its own physical laws, dimensions, and timelines. In this sense, the death of our universe might not be an end, but a transformation, a fertile ground from which others might bloom, born not from order, but from chaos. The dominance of quantum foam may also hint at the ultimate fate of information. If all that exists is probability and flux, then perhaps all information is smeared into the very nature of the foam. No longer stored in particles or fields, it becomes part of the ebb and flow of potentiality itself. The history of the universe, in this view, is not lost. It is rendered as interference patterns and fleeting correlations in a sea of quantum uncertainty. In such a realm, energy itself might not be meaningfully defined. Classical notions of temperature, mass, and motion dissolve. What remains is potential, the raw, flickering readiness for something to happen, even if nothing stable ever does. The foam bubbles and pops in random directions, not guided by thermodynamic gradients or gravitational forces, but by the inherent unpredictability of quantum spacetime. At the edge of our understanding, physicists struggle to describe this era. Our current models, quantum mechanics, general relativity, even string theory, may not suffice. The merging of gravity and quantum mechanics, still incomplete, becomes essential in this context. Without it, we can only speculate about the properties of this ultimate ground state of the cosmos. But even in that speculation lies a profound mystery, that the end of everything might not be nothingness, but noise, noisy space, noisy time, and noisy reality. In such a state, what would existence mean? Could consciousness, if it somehow survived, make sense of a universe where nothing lasts and nothing is real in a stable way? If all is foam, then observation itself becomes meaningless. There is no observer, no object, and no distinction between them. Only fluctuations, endlessly recursive, endlessly uncertain. Perhaps this quantum sea is not just the end, but also the beginning. Some cosmologists theorize that the universe we know may have arisen from such a foam, an energy fluctuation that inflated into a cosmos. If so, then this distant future may mirror the ancient past. The trillion-year mark might not be the final stage, but a return to the primordial condition, a reset, not unlike the calm before the Big Bang storm. And if time itself becomes meaningless, then duration may not apply. The quantum foam may last forever, or it may flicker for an instant before triggering a new inflationary burst. It may be the womb of eternity or the twitch of finality. Without stable space-time, there's no reference point, no way to know what a trillion years even means anymore. The quantum foam dominance scenario thus forces us to confront the limits of human comprehension. We are being shaped by order, pattern, and continuity. This final state of the cosmos, if it comes to pass, would obliterate all of that. It is the unstructured void, not made of emptiness but of ceaseless, meaningless motion, a turbulence without direction, a noise without sound. In the end, the most haunting truth may be that this chaotic foam is the default condition of reality, and everything we consider structured, the galaxies, the laws of physics, even consciousness, was a fleeting anomaly. The universe, as we know it, might have been a brief bloom on the surface of an eternal, turbulent sea. And in the silence of the far future, the sea returns and the bloom fades away. The idea of a false vacuum bubble expansion is one of the most unsettling possibilities in theoretical physics. It stems from the notion that our universe may not reside in the most stable possible state of energy, but rather in a metastable configuration, a false vacuum. This is akin to a ball resting in a shallow depression on a hill, appearing stable but not truly at rest. Given enough time or sufficient perturbation, it could fall into a deeper, more stable valley. In the cosmic sense, this means that all the fundamental forces, particles, and constants we know might be artifacts of this temporary vacuum state. If a lower energy, more stable vacuum state exists, then a transition could eventually occur, and when it does, it may unmake our universe in the blink of an eye. Such a transition would begin with a tiny region, a bubble, where this true vacuum forms. Once initiated, this bubble would expand at the speed of light, converting everything it touches into a new and unfamiliar form of reality. Nothing could outrun it, and no warning could precede it. All matter, forces, atoms, and even the fabric of space-time itself will be rewritten by the new vacuum state. To anything within its path, existence would simply end, instantaneously, painlessly, and absolutely. And from a cosmic standpoint, it could happen at any moment. What's more chilling is that the odds of this catastrophic shift increase over time. 1 trillion years is an immense duration, enough for even extraordinarily rare quantum events to occur. With no way to predict when or where such a bubble might form, we are left with the realization that the universe could be living on borrowed time. The longer it endures, the greater the cumulative probability that this transformation will occur. A vacuum bubble could already be expanding toward us from some distant region of space, its approach inevitable, invisible, and unstoppable. This possibility stems from the theoretical framework of quantum field theory, particularly the Higgs field. After the Higgs boson was discovered, calculations suggested that the universe might be perched precariously in a metastable state. If those calculations are correct, then the true vacuum lies somewhere deeper in the energy landscape, waiting to be accessed by quantum tunneling, a random, probabilistic leap from our current state to the lower one. The odds are minuscule per unit of time and space, but the universe is vast and time is long. If such a vacuum transition does occur, it wouldn't merely destroy familiar particles. It would alter the very laws that govern them. Constants like the speed of light, the strength of gravity, or the mass of the electron might shift, rendering chemistry, biology, and structure itself impossible. Protons could become unstable, electrons might vanish, and even space could crumple into configurations we can't comprehend. The universe we know, its history, its complexity, its narrative, would be wiped clean and replaced with alien physics. The expansion of a false vacuum bubble is not limited by any force we understand. It wouldn't burn, crush, or implode the universe. It would replace it. The distinction is subtle but profound. It doesn't cause destruction in the traditional sense. Instead, it rewrites existence with a new set of rules, a different symmetry, and potentially an entirely new kind of reality. Whether or not this new realm would support anything resembling matter, time, or consciousness is unknowable. In this scenario, entropy, the arrow of time, and thermodynamic decay become irrelevant. The progression of heat death, black hole evaporation, and cosmic loneliness would never complete. A false vacuum transition bypasses all natural aging processes. It is the ultimate cosmic interrupt, a reset that doesn't just erase the past, but renders it meaningless in the context of what follows. The universe wouldn't just end, it would be redefined. Moreover, the spread of such a bubble is absolute. There is no shielding, no escape. The speed of light serves as the upper limit of travel, so nothing can outrun or evade the transition. Even if some advanced civilization detected the oncoming wall of new reality, it could do nothing but acknowledge the inevitable. All knowledge, memory, and meaning would vanish, absorb into a new framework of existence that bears no resemblance to our own. For all its horror, this possibility also presents a kind of cosmic purity. It removes the slow, melancholic fade of entropy and replaces it with clarity, a sharp and final punctuation mark in the long story of being. And just as unsettling, this punctuation could come at any point, utterly disconnected from cosmic time or galactic events. The stars may shine, galaxies may spin, and life may thrive, until they don't, extinguished not by decay, but by transformation. And yet, it's possible that our universe has already survived countless such potential transitions. The quantum field's underlying reality may have fluctuated near the boundary of stability without ever tipping over. Each passing trillion years may suggest not inevitability, but resilience. Or perhaps we're simply waiting, balanced on a razor's edge, and the longer we last, the more likely we are to fall. A trillion years hence, the universe may still be quiet, cold, and aging. Or it may already have succumbed to the false vacuum, its prior state long forgotten in the new order of things. Perhaps, in some deep sense, this is how new universes are born, not through expansion alone, but through collapse and renewal via the redefinition of physical law. What begins as a catastrophe may become the seed of a new cosmos. This lends the false vacuum theory a strange duality. It is both the death of everything and potentially the birth of something else. We may never know what lies on the other side of such a transformation. But if it comes, we will not see it, fear it, or feel it. It will simply be the end, swift, absolute, and transcendent. The holographic principle, a radical idea born from black hole physics and string theory, suggests that all the information in our three-dimensional universe may actually be stored on a distant two-dimensional surface, perhaps at the edge of the cosmos. Our reality, in this model, is not fully real in the traditional sense, but a projection from that encoded information, much like a hologram emerges from a laser-etched plate. If this concept holds true, then the entire universe we know, its galaxies, stars, thoughts, and time, are part of an elaborate, dimensional mirage, rooted in data written on a cosmic boundary. But even the most sophisticated holograms are vulnerable to degradation. Over 1 trillion years, if that boundary begins to lose coherence through entropy, instability, or some deeper cosmic process, the projection it sustains could start to fail. This fragmentation wouldn't resemble traditional decay, like stars burning out or particles breaking down. Instead, it would resemble a digital system slowly losing resolution, where the fidelity of reality itself begins to unravel. Matter might subtly blur. Particles may flicker or behave inconsistently. Physical laws could become probabilistic, not due to quantum uncertainty, but because the code behind them is breaking. At first, the changes might be undetectable, mere fluctuations at the edge of perception. But over time, errors in the holographic code could cascade. Structures in space might dissolve, not because they've eroded, but because the data that constructs them has become corrupted. Galaxies could disappear like corrupted files. Light might bend unnaturally, not due to gravity, but because the code rendering space has glitched. Even consciousness could be affected, with minds experiencing distortions in memory, logic, or time itself, not due to biological decay, but due to misrendering of informational patterns. This fragmentation could be patchy, affecting different regions of a universe unevenly. Some areas may retain perfect coherence for quadrillions of years, while others become cosmic dead zones, places where physics stops making sense. These rifts in the holographic fabric might become the new dark matter, undetectable through traditional means, but warping space and behavior through broken logic. The universe, in this view, becomes less a grand machine and more an aging simulation, one that is slowly forgetting how to sustain itself. If reality is code, then like any long-running program, it is vulnerable to memory leaks, fragmentation, and eventual collapse. The cosmic substrate holding the universe together might be finite, limited by rules we don't yet understand. After enough time, even perfect code could suffer from instability. Perhaps external factors, interactions with other universes, or fluctuations in the underlying structure, introduce errors, causing portions of the projection to decay or misalign. Some theorists believe that black holes may serve as nodes or storage sectors of the holographic data grid. Over immense time, as black holes evaporate and disappear, they might take with them key components of the universe's underlying structure. If those areas of the holographic boundary were responsible for maintaining specific information, mass, force laws, geometry, then their loss could result in tangible fragmentation of reality across vast regions. This leads to the eerie possibility that entropy in a holographic universe doesn't just mean heat death or stillness, but literal digital corruption. Not a cold, dark universe, but a glitched one, where stars freeze mid-collapse, time loops inconsistently, and regions become unrecoverable like corrupted sectors of a hard drive. Our current reality might already contain hints of this. Irregularities in cosmic background radiation, unexplained anomalies in particle behavior, whispers of deeper issues beneath the projection. In such a scenario, the end of the universe is not marked by silence or destruction, but by incoherence. Structures fall apart not from force, but from lack of informational clarity. Physics doesn't end with a bang or a fade. It dissolves into noise, where the rules that once governed everything dissolve into undecipherable data. The boundary, once precise and elegant, becomes frayed, no longer able to hold the infinite illusion it once projected. Yet, this fragmentation may not be a terminal failure. It could mark a transition, a reformatting of the holographic boundary, perhaps leading to a reinitialization. Just as data corruption can sometimes lead to new patterns, a broken universe might become the seedbed of new laws, new structures, or entirely different realities. The pixelation of space might eventually condense into a new order, a rebooted universe written in a different syntax. Alternatively, we might be seeing only one layer of the holographic onion. If this projection fails, a deeper layer may take over. The decay could reveal truths hidden for eons about what reality actually is, where consciousness resides, and whether time is a construct or consequence. In that sense, fragmentation is not the end, but the unveiling of a greater stage. Still, from our perspective, the slow corruption of the holographic code would feel like a haunting unraveling. The stars that once burned with clarity might shimmer like digital ghosts. Planets may lose cohesion, their surfaces glitching as if caught in a stuttering frame. Mathematics itself might yield contradictions. Space could fold in on itself, not through gravity, but through failing logic. And in the midst of this, any remaining intelligence might face the greatest existential question. What does it mean to die in a simulated universe? As time progresses into the incomprehensible trillions, this cosmic mirage may shatter entirely. What lies beyond is unknown, perhaps nothing, perhaps something fundamentally other. If the universe is a hologram, then it is also a story written in code, and all stories eventually must come to an end or be rewritten. In the farthest reaches of time, when the last stars have died and black holes have evaporated, a strange kind of silence will fall over the universe. Not of emptiness, but of particles moving unseen and undisturbed. Chief among these final cosmic remnants may be neutrinos, nearly massless, electrically neutral, and interacting with matter so rarely that billions pass through your body every second unnoticed. Neutrinos are nature's ultimate survivors. In a universe a trillion years old, where most familiar structures have dissolved, neutrinos may form the dominant presence, an invisible fog stretching across all of space. Unlike baryonic matter, which decays and collapses, or photons, which redshift into undetectable wavelengths, neutrinos endure. They decouple from matter early in the universe's history and travel vast distances with barely any interaction. As everything else dims and dies, neutrinos continue on, practically unaffected. Over trillions of years, their numbers accumulate into a sea of ghostly movement, motion without sound, presence without form. This neutrino fog wouldn't resemble a traditional cloud. It wouldn't cast shadows or reflect light. It wouldn't collide with planets or be pulled by gravity into visible shapes. It would be diffuse, stretching across intergalactic voids, passing through dead galaxies and black hole remnants alike. A silent tide of subatomic particles, it would be the only trace of energy still coursing through space. Even the cosmic microwave background, the faint echo of the Big Bang, would have stretched to such long wavelengths that it becomes undetectable. The only relic of the universe's fiery origin might be the cosmic neutrino background, a counterpart to the microwave background, though far colder and harder to detect. It is thought that these relic neutrinos still exist even now, but in the deep future, their relative prominence may increase dramatically as more massive forms of matter vanish. Quantum decay processes, like proton decay, if it occurs, would contribute additional neutrinos to the fog. As atoms break apart, they release these ghost-like particles, quietly adding to the growing sea. Black hole evaporation through Hawking radiation might also release neutrinos. Each event is minuscule and spread out over unimaginable timescales. But given enough time, the universe becomes a machine for producing nothing but neutrinos and entropy. Over a trillion years, this ghost universe becomes harder and harder to observe, not because of distance or darkness, but because of the nature of its contents. Neutrinos are infamous for evading detection. It takes massive detectors buried deep underground just to catch a few per day now. In the far future, there may be no observers, and even if there were, the tools needed to perceive reality would be utterly useless. The physics of such a universe would be dominated not by motion or structure, but by statistical drift. Neutrinos, constantly in motion at nearly the speed of light, would form a kinetic haze. There would be no thermodynamic equilibrium, no localized systems, only a slow statistical wash of particles occasionally scattering, rarely enough to matter. The universe, in this form, is a slow simulation of energy loss and motion without consequence. In a poetic sense, the neutrino fog represents the final breath of the universe. Not with a bang, not even a whimper, but with an endless exhalation of ghost particles spreading into infinity. Time still moves forward, but events no longer register. Structure no longer forms. Only the fog remains, motion without memory. Yet even this neutrino-dominated epoch is not eternal. The expansion of the universe continues, stretching all wavelengths of energy. Over time, neutrinos themselves will redshift, their energies diluting even further. Those that were once fast and lively will slow relative to cosmic expansion, becoming ever more rarefied, ever more difficult to trace. Eventually, they may become too stretched to ever interact again, an ultimate dispersal into isolation. There's also the unknown. Neutrinos, though weakly interacting, may undergo transformations or decay into lighter, undiscovered particles over extreme timescales. If neutrinos are not truly stable, then even this final fog may thin and fade. Perhaps the universe does not end with neutrinos, but with whatever lies beyond them, if anything. In this quiet epoch, the idea of structure loses meaning. There are no stars to orbit, no atoms to bond, no black holes to fall into. Physics itself becomes less about forces and more about possibilities. Statistical occurrences in an environment so sparse that events are geological in rarity. Intelligence, should it ever reemerge or persist, would need to rethink existence entirely, grounded not in matter or energy, but in probability itself. The neutrino fog also raises the question of perception. What does a universe look like when there is nothing left to see? If observation defines reality, then the fog marks a turning point where perception itself becomes impossible. The universe continues, but in a form no longer compatible with awareness or interaction. Ultimately, the age of neutrinos would be a time of quiet finality, not a graveyard of what once was, but a drifting field of what remains. Tiny, indestructible particles moving endlessly through a dying cosmos. It is a phase where the grandeur of galaxies and the brilliance of stars are long forgotten, replaced by an ocean of motion that no longer builds, changes, or remembers. And so, in the vast span of cosmic time, the neutrino fog may not just be the last breath of the universe. It might be its echo. In a distant cosmos where the trillion-year mark has long passed, the structure of the universe has changed so drastically that the very concept of boundaries has ceased to exist. No longer are there dense clusters of matter to warp space enough to trap light. Black holes, once the final dominators of gravitational complexity, have long since evaporated through the slow and steady process of Hawking radiation. With their disappearance, so too vanish the last true event horizons, those invisible barriers beyond which no information could return. The universe now is open in the most profound sense of the word, with no curtains drawn across space-time, no regions from which nothing can escape. Every photon, no matter how weak or ancient, now has a free and endless trajectory across a vast, desolate void. In this no-event horizon universe, transparency reigns. There are no cosmic structures dense enough to distort or devour light. The light that does exist is ancient, diluted, and redshifted beyond recognition. Its energy stretched thin across the yawning chasm of expansion. This light no longer carries information in any familiar sense. It's like the fading whispers of a party long since over, still echoing across abandoned halls where no ears remain to hear. Every particle of radiation travels unobstructed across endless space, but its message is lost, swallowed, not by darkness, but by irrelevance. The loss of event horizons is more than just the disappearance of physical thresholds. It represents the end of separation itself. Without gravitational traps, the universe has no true boundaries between here and there. Everything is connected by the potential of observation. Yet paradoxically, there's nothing left to observe. This universe is a hyperbolic mirror of clarity, fully transparent, yet ultimately featureless. Each region of space now resembles every other, with no concentration of matter to break the monotony, no heat gradients to birth complexity, no movement left to animate the void. Temperature in this epoch approaches the theoretical limit of absolute zero. Thermal motion is a memory. Energy gradients have been smoothed out into nothingness, and time itself seems to move without consequence. With no horizons to limit the influence of light or gravitational fields, every point in the universe is technically visible to every other, though there is nothing left worth seeing. It is an ironic form of perfect visibility in which the viewer and the view have both vanished into irrelevance. This hypertransparent cosmos would be unlike anything we could ever truly imagine. The laws of physics, as we know them, may still operate in principle, but they have no meaningful application without structures to act upon. Gravity remains, but only as a ghost. Its influence stretched so thin that it no longer bends anything. Electromagnetism persists, but without atoms or charged particles to manipulate. Quantum fluctuations may still emerge briefly from the fabric of space-time, but even these are faint and pointless against the backdrop of nothingness. Philosophically, the no-event horizon universe represents a sort of cosmic nakedness, an ultimate unveiling where every secret has already been laid bare and no mysteries remain to be uncovered. It's a state where the entire cosmos has become a single, continuous, unified medium, homogeneous in both structure and significance. No walls remain to block the flow of time or light, and yet nothing flows. The transparency becomes oppressive in its completeness, as if the very soul of the universe has been wrung dry of story, character, and change. Communication, too, becomes meaningless. In a cosmos without obstructions, you might think messages could travel forever. But in this scenario, there's no one left to send them, no one left to receive. The signals that do remain are so degraded, so energy-deprived, that they can't be distinguished from background noise. The concept of a background itself dissolves in a universe where no structures stand out against anything else. Everything is the same, everywhere, always. The no-event horizon universe also carries implications for the arrow of time. If time is in part defined by entropy gradients and observable events, then in a cosmos devoid of horizons and structure, does time still have a direction? Or does it become static, meaningless, a coordinate label on a dimension that no longer produces cause or effect? Some physicists argue that without contrast, without memory, without eventful change, time would cease to have practical meaning. It would stretch into infinity not as a journey, but as a featureless line. Moreover, this epoch would challenge even our most speculative technologies and ideas about survival. Civilizations, if they could somehow persist into this age, would find no refuge in energy or matter. They would be unable to gather power, communicate across meaningful distances, or even distinguish themselves from their surroundings. The no-event horizon universe is the death of distinction, the dissolution of separation, the end of things being this rather than that. It's not the firework ending of the Big Rip or the solemn chill of heat death. It is the quietest of all cosmic conclusions. The implications extend to cosmological models as well. Without event horizons, the causal structure of the universe simplifies. Every point can influence every other, albeit in trivial, non-discernible ways. The cosmic web that once defined the universe's structure is no longer woven, but dissolved. We return to a state resembling the earliest moments after the Big Bang, but inverted, not pregnant with potential, but barren of it. Instead of a hot, dense, chaotic beginning, it's a cold, diffuse and lethargic end. Even in its total emptiness, the universe may not be truly still. The very fabric of space could still undergo subtle shifts, quantum tremors without consequence. These may never give rise to anything substantial again, but they remain as a kind of residual flicker, like the final glow of a star collapsing into oblivion. The no-event horizon universe is then not truly dead. It simply no longer lives in any way we would recognize. The legacy of such a cosmos may exist only in theoretical frameworks and mathematical possibilities. To observers that can no longer exist, it offers nothing. To equations, it is a possible endpoint, an eternal moment stretched over infinite stillness. A trillion years from now and beyond, the universe may find itself not in a blaze of entropy or a scream of collapse, but in this silent, uninterrupted transparency, a conclusion not of destruction, but of complete, final openness. In a universe aged beyond a trillion years, not only do stars fade and particles scatter, but memory itself, woven into the fabric of matter and structure, dissolves. The past, once recorded in the orbits of planets, the spectra of stars, the scars of cosmic collisions, and the arrangement of galaxies, begins to fade as its vessels disintegrate. Entropy doesn't just erase form. It erodes the very capacity for remembrance. Every moment in history depends on some configuration of matter to preserve it. A library, a fossil, a photon bouncing off a surface, all are repositories of memory. But over cosmic timescales, these configurations break down. Black holes, once considered the ultimate memory vaults due to their theoretical information storage on event horizons, have evaporated. Neutron stars, once dense archives of collapsed time, have cooled into invisibility. Even radiation, stretched across the expanding void, loses coherence, its original message drowned in thermal noise. By a trillion years, the universe's grand narrative has been lost to physical amnesia. No atoms remain arranged in ways that tell a story. Molecular patterns, whether in organic life, crystalline formations, or digital media, have long since crumbled. The gravitational arrangements of galaxies that once formed cosmic memories, traced back by humans to reconstruct the Big Bang, have unraveled into randomness. No star charts exist. No observers remain. No evidence, even indirect, can be recovered. This decay is not sudden, but insidious. It begins with minor perturbations. Atoms jiggle, structures degrade, energy leaks. Over time, even the most stable materials are reduced to disorder. A silicon wafer storing a trillion memories is still bound by the same universal laws as a drifting asteroid, inevitably disassembled by entropy. Given enough time, all differences fade, all memories blur. Every specific arrangement that encoded knowledge becomes indistinguishable from chaos. Even quantum memory, entanglement, coherence, exotic states that once stored information at the smallest scales, eventually succumbs to decoherence in a thermal sea of nothing. The very possibility of retrieving or reconstructing past states disappears. The universe forgets not because of violence or collapse, but because forgetting is the natural consequence of infinite duration. This isn't merely the absence of minds to remember. It is the annihilation of the conditions for memory itself. There is no more pattern, no more differentiation, no more signal. The cosmic medium becomes uniform not just in structure, but in implication. A trillion years hence, the universe doesn't remember stars or galaxies or thoughts or lives. Not because it chooses to forget, but because there is nothing left with which to remember. And yet, this loss of memory is total only from within, from an external or abstract perspective, one removed from the arrow of time. Some theoretical physicists argue that information might still be preserved in the initial conditions of the cosmos. But within the lived reality of a decayed universe, no trace remains. Time itself, having delivered everything to entropy, now stands over a smooth, silent void, stripped of recollection. In the end, Universal memory decay is not the destruction of history, but its dissipation. The cosmic story isn't burned, it fades. It doesn't end in punctuation, but in ellipsis. The echoes of existence are scattered into irretrievable entropy, and the universe, vast, cold, and ancient, remains, but with no shadow left of what it once was. The structure of our universe may not be limited to the three dimensions we perceive. Many advanced physical theories, especially those grounded in string theory or M-theory, suggest the existence of extra spatial dimensions, tightly curled or hidden from everyday experience. While they may be stable now, nothing guarantees their permanence. Over cosmological timescales, these dimensions might not remain frozen. Instead, they could stretch, twist, collapse, or rupture. In a universe age beyond 1 trillion years, the very geometry of existence might begin to shift, not just within the visible cosmos, but in the hidden scaffolding beneath it. In this scenario, the fourth spatial dimension, or others beyond it, may begin to deform. These extra dimensions, once stable and compactified at subatomic scales, may unravel due to unknown instabilities or fluctuations. A collapse of even a single extra dimension could have devastating effects. The physical constants we take as fixed, like the strength of gravity or the behavior of electromagnetic forces, depend on the structure of these dimensions. A dimensional collapse could warp these constants beyond recognition, erasing the foundational laws of physics as we know them. As the fourth dimension buckles, space itself might lose its integrity. Distances would distort unpredictably. Regions of space that were once stable could experience bizarre geometric shifts, shrinking, stretching, or twisting into unrecognizable forms. The fabric of reality might no longer behave like a uniform grid, but more like a crumpled origami, folding in ways that defy our current understanding. Structures that once seemed eternal, such as voids, clusters, or even dark matter scaffolding, could dissolve into dimensional confusion. In such a future, three-dimensional objects, including matter, might not survive. If higher dimensions undergird the formation and stability of particles, their collapse could cause atoms to lose cohesion. Electrons might no longer orbit nuclei in predictable shells. Protons and neutrons could fall apart or mutate into exotic states. Familiar forms, solids, gases, stars, might become impossible. The physical universe would dissolve into a bizarre dimensional haze, where geometry itself no longer behaves rationally. Even the passage of time might suffer. If time is entangled with spatial dimensions through relativity, then changes to space could ripple into time's flow. Time might stretch irregularly, loop in strange ways, or stop altogether in some regions. The arrow of time, already threatened by entropy, could become incoherent as the universe spirals into a metastructural failure. Observers, if any could exist, would find reality breaking down not into nothingness, but into something alien. Particles might flicker in and out of existence, not due to quantum uncertainty, but due to collapsing dimensional frames that can no longer support them. The universe might not look empty, but shattered, full of ghost-like remnants, partial realities, and warped rules. Structures that once obeyed causality and locality could begin to violate them. Particles might interact across vast distances without mediation, or events could unfold in patterns inconsistent with linear progression. The collapse of dimensional stability would mean a breakdown in the principle that space and time are coherent and continuous. Instead, reality might become a disjointed collage of fragments, stitched together by remnants of a once stable metric. Over time, as the collapse deepens, what remains might no longer be recognizable as a universe. It would not be empty, but incoherent, a dreamlike state of physics, where events no longer unfold but stutter, loop, or diverge. Light may still exist, but without distance or direction, it would be meaningless. Matter, stripped of dimensional support, may dissolve into informational noise, no longer held together by space-time coherence. In such a fate, the very idea of somewhere or sometime would cease to be meaningful. The map of the cosmos would fold not into darkness, but into abstraction, where nothing can be measured, compared, or remembered. A trillion years would not lead to stillness, but to spatial delirium, a collapse not of matter or energy, but of framework and form. And in the end, if dimensions fold too tightly or collapse entirely, the entire observable reality may vanish, not destroyed in an explosion or faded into emptiness, but erased from within. Like a page that forgets its own margins, the universe could silently blink out, leaving not even the idea of its own existence behind. The universe as we know it depends heavily on certain physical constants, values like the speed of light, Planck's constant, the gravitational constant, and the fine structure constant, that have held steady for billions of years. These constants govern everything from the behavior of atoms to the expansion of the cosmos. But what if these numbers, which we treat as immutable, begin to shift over unfathomable timescales? The deconstruction of constants theory suggests that after a trillion years, these fundamental constants may start to drift, even if only by infinitesimal amounts. Such tiny shifts could lead to profound consequences, altering the very fabric of reality. Matter could cease to behave as expected. Atoms might no longer hold together, or light itself could lose its familiar properties. Imagine the fine structure constant, which determines the strength of electromagnetic interactions, changing by a fraction. This would affect how electrons orbit nuclei, potentially making stable atoms impossible. Chemistry, as we understand it, would collapse. The interplay between forces that once held matter together could become unpredictable, and the building blocks of the universe might dissolve into something completely alien. Over the course of a trillion years, as these constants gradually deconstruct, the universe's predictable rules might unravel, rendering familiar matter into chaotic, unrecognizable forms. Energy itself could transform in surprising ways. The cosmological constant, linked to the energy density of empty space, might alter, accelerating or decelerating cosmic expansion in unanticipated manners. Such changes could either hasten the universe's march toward entropy or, paradoxically, stall it. This deconstruction might mean that physics becomes more fluid and less deterministic, introducing new phenomena that defy our current understanding. The laws that once explained gravity, electromagnetism, and quantum mechanics could morph into something strange and alien. Even time and space might be subject to these shifts. If the speed of light changes, the causal structure of the universe would be affected. Signals that once traveled at a universal speed limit might vary, causing the flow of time to warp or distort. This would have cascading effects on everything from particle interactions to the grand-scale geometry of the cosmos. The smooth fabric of space-time envisioned by Einstein's relativity might become irregular, fluctuating as constants slide out of their historic values. The implications extend deeply into cosmology and astrophysics. Stars, if any remain, would burn differently or not at all. Gravitational attraction might weaken or strengthen erratically, disrupting the orbits of any remaining objects. Galaxies could fragment or collapse in unexpected ways. The universe might end up looking less like the vast, mostly empty cosmos we imagine, and more like an unstable, fluctuating sea of energy and matter where nothing is stable for long. Fundamentally, the idea of universal constants changing challenges the core assumption that the laws of physics are eternal and universal. It suggests a dynamic cosmos where even the bedrock of reality isn't fixed, but instead subject to slow decay or evolution. This may be driven by quantum processes, interactions with unknown fields, or properties of space-time that only reveal themselves over vast, almost unimaginable timescales. The universe's constants could thus be as transient as the stars that have long since died. One can imagine this deconstruction as a cosmic erosion, not of matter or energy, but of the very rules that govern them. Over a trillion years, the universe might degrade from a well-ordered system into a strange, unstable state where cause and effect become unreliable and physical phenomena lose their coherence. Our current scientific frameworks might be rendered obsolete, replaced by new, unrecognizable principles that govern a radically altered cosmos. This scenario also raises philosophical questions about permanence and change. If the constants of nature can vary, then the universe is not an eternal monument, but a living system subject to decay and transformation at every level. Such a perspective aligns with some speculative ideas in theoretical physics, suggesting a multiverse or dynamic landscape of physical laws that can evolve or mutate, leading to universes vastly different from our own. This view also offers a poignant image of cosmic impermanence. Everything we hold to be fixed, the laws that dictate how particles behave, how stars shine, how gravity shapes space, might dissolve into a twilight of uncertainty, leaving behind a universe that no longer supports the familiar structures or phenomena that make it intelligible. The deconstruction of constants marks not just an end to life and matter, but an end to the stable rules that make existence meaningful. In practical terms, measuring or observing such a slow drift in constants is beyond current capabilities, requiring timescales far greater than the age of the universe. But as a theoretical exploration, it opens new horizons for understanding the ultimate fate of the cosmos. The universe's physical framework may not be permanent, but a temporary state in a much larger, ongoing cosmic evolution. After 1 trillion years, if this theory holds true, we might find ourselves in a cosmos where nothing behaves as it once did. Particles may not form stable structures. Energy might dissipate in unknown ways. The familiar interplay of forces might be replaced by a chaotic stew of fluctuating parameters. It's a picture both unsettling and fascinating, reminding us that the universe's future is as mysterious as its origins. The deconstruction of constants is thus a humbling reminder of a universe's fragile balance. The constants we rely on to understand reality are not guaranteed to persist forever. Their potential drift over unimaginable time frames may herald a new cosmic era, one marked not by heat or cold, entropy or order, but by the very unraveling of the fundamental scaffolding of nature. In this distant future, the universe may lose its identity as a stable, knowable place and become an ever-changing, shifting sea of physical parameters. It might no longer make sense to talk about laws of physics at all, but only about transient conditions that emerge and dissolve in a constantly evolving cosmic landscape. Thus, the universe at 1 trillion years could be the setting of a profound transformation, not just in matter or energy, but in the very essence of reality itself. The constants that define existence could slip away, leaving behind a cosmos so alien that it defies all attempts at comprehension. The ultrastable remnant theory paints a picture of the far future universe, populated not by stars, galaxies, or even familiar particles, but by extraordinary, nearly eternal forms of matter that withstand the relentless passage of time. While most ordinary matter gradually decays, evaporates, or dissolves into radiation and subatomic particles, this theory proposes that certain exotic states might resist entropy's pull indefinitely. Strangelets, hypothetical small droplets of strange quark matter, are one candidate. Unlike ordinary atomic nuclei, strangelets could be stable or metastable due to their unique core composition, enabling them to survive processes that dismantle conventional matter. These strangelets, if they exist, could be incredibly dense and stable, drifting through the cosmos like cosmic relics from an earlier, more energetic epoch. Their resilience might allow them to outlast stars, black holes, and even fundamental particles that normally decay over eons. As the universe continues to cool and grow dark, strangelets would be some of the few survivors, floating silently through the expanding void, carrying with them a memory of the cosmos' exotic past. Cue balls are another fascinating candidate for ultrastable remnants. These hypothetical, non-topological solitons, predicted by certain theories beyond the standard model of particle physics, could be composed of scalar fields that hold vast amounts of energy in a stable configuration. Their stability arises from conservation laws that prevent them from decaying easily, making them resilient survivors in a universe otherwise falling apart. If such objects persist, they might become the universe's final islands of structure and energy. The presence of these ultrastable remnants changes the picture of cosmic destiny dramatically. Instead of a cold, empty vacuum devoid of matter, the universe could remain dotted with these long-lived, dense particles. Though sparse and isolated, they might interact weakly with other particles, possibly seeding rare events or phenomena even in an otherwise desolate cosmos. Their interactions would be subtle, but their survival would defy the otherwise total decay of matter. As a trillion years pass, these remnants could dominate the mass budget of the universe's remaining matter, becoming the last testament to the complexity and variety of physical states that once thrived in a hotter, more active cosmos. They may drift through the emptiness, barely interacting, yet persisting far beyond the lifetime of any star or black hole. These remnants also raise intriguing questions about the universe's informational content. Because they survive so long, they could encode rare physical properties or histories from the universe's earlier phases, effectively serving as cosmic time capsules. If they contain traces of fundamental physics or early universe conditions, then studying such remnants, if ever possible, might reveal secrets lost to most of the universe's history. The formation and stability of these exotic objects depend on the deep details of particle physics and cosmology, many aspects of which remain speculative or beyond current experimental reach. Yet, their theoretical existence offers a compelling alternative to the idea of total decay. They embody the possibility that the universe, while transforming beyond recognition, might preserve some islands of order and substance against the tide of entropy. Their persistence challenges assumptions about finality. While stars burn out and black holes evaporate, and ordinary matter succumbs to decay, ultrastable remnants hint at a form of matter that is fundamentally resistant to time's erosive power. This survival would suggest the universe never quite reaches absolute nothingness. Instead, it retains traces of complexity in the form of these extraordinary objects. Moreover, the existence of ultrastable remnants may have implications for the ultimate fate of information. While conventional matter degrades, these remnants could lock in information encoded in their structures, preserving fragments of cosmic history far longer than any other physical entity. This could provide a subtle but persistent imprint of the universe's past in a future otherwise dominated by darkness and decay. Interestingly, if these remnants interact with one another at all, even weakly, their slow dynamics over trillion-year timescales might give rise to rare but profound events. Collisions or mergers of strangelets or cue balls could release bursts of energy or trigger transformations that briefly illuminate the dark cosmos, acting as distant echoes of a universe long past. Their ultrastability may also hint at physics beyond the standard model, involving new forces or conservation laws that protect their integrity. Discovering evidence of such particles in the present or future would revolutionize our understanding of matter and the universe's long-term evolution. Despite their elusive nature, the prospect of such particles existing motivates continued theoretical and experimental investigations in particle physics and cosmology. Understanding their properties could shed light on the ultimate resilience of matter and the complex pathways the universe might take as it ages beyond recognition. In a universe dominated by these ultrastable remnants, the landscape would be vastly different from our current cosmos. The void would be punctuated by tiny, dense specks of matter, relics of cosmic evolution that neither shine nor decay, but persist indefinitely. These remnants would drift endlessly, marking the final chapters in the saga of existence. In essence, the ultrastable remnant theory offers a vision of cosmic longevity where some forms of matter achieve near immortality. They stand as silent guardians of the universe's distant past, enduring when nearly everything else has succumbed to entropy's relentless advance. The fate of the cosmos, in this view, is not absolute oblivion, but a slow fade into a realm populated by these rare, extraordinary survivors. Dark energy, the mysterious force driving the accelerated expansion of the universe, is typically considered a constant, smoothly permeating all space. However, this assumption may be an oversimplification. Some theoretical models suggest that dark energy could undergo a phase change, similar to how water transforms between solid, liquid, and gas under certain conditions. This phase transition would represent a fundamental shift in the nature of dark energy itself, altering how it interacts with space and matter. If such a phase change occurs, it would dramatically affect the cosmic expansion rate, potentially reversing, accelerating, or otherwise modifying it in ways that could reshape the universe's large-scale structure. Over the course of 1 trillion years, the cumulative effects of dark energy's influence become profound. If the energy density or pressure associated with dark energy changes abruptly, it could shift the universe from steady accelerated expansion into a new regime. This might manifest as a rapid contraction phase, where the expansion halts and reverses, causing galaxies, stars, and matter to draw closer again. Alternatively, it could trigger an even faster expansion rate, far exceeding current predictions, ripping space apart with violent consequences. Either scenario would fundamentally redefine the cosmic landscape, obliterating structures, creating new horizons, or compressing all matter into previously unimagined densities. A phase transition in dark energy would not merely affect expansion speed, but also the very fabric of space-time. As the vacuum energy shifts, the curvature and topology of space could transform, potentially generating phenomena like cosmic domain walls, new particle horizons, or exotic forms of space-time geometry. These changes would ripple across scales, from vast intergalactic voids down to quantum fields, impacting matter, radiation, and fundamental forces. The universe's future would be marked by epochs unlike anything observed in its past, dominated by new physical laws emerging from this altered dark energy state. At the trillion-year mark, these changes could be underway or imminent, representing a pivotal turning point in cosmic evolution. If dark energy's equation of state parameter, describing its pressure relative to energy density, crosses critical thresholds, it might signal the onset of this phase transition. This threshold crossing could be subtle or sudden, but its effects would cascade through the universe, fundamentally altering its fate. In some models, dark energy's phase change might cause spatial dimensions to stretch unevenly, potentially giving rise to anisotropic expansion where different directions grow at different rates. This would distort the shape of cosmic structures, warp light paths, and challenge our notions of homogeneity and isotropy that underpin modern cosmology. Over immense timescales, the universe might evolve into a patchwork of regions with distinct expansion histories, fragmented by the boundaries formed during this phase change. If the phase change compresses space, the consequences would be just as dramatic. Previously dispersed matter could be driven back together, increasing density and temperature. This compression might reignite particle interactions, collapse remnants into new compact objects, or even trigger a cycle of renewed star formation or black hole genesis on scales beyond current imagination. Such a reversal could temporarily breathe new life into a cosmos otherwise heading toward desolation. Conversely, if the phase change increases the repulsive force of dark energy, it could accelerate the Big Rip scenario. Structures that survived until now might be torn apart at an even faster rate, atoms and subatomic particles shredded as space expands faster than any force can hold them together. In this regime, no known matter or energy could persist beyond a certain epoch, and the universe would fade into a nearly empty, featureless expanse even sooner than predicted by current models. The mechanics of the dark energy phase change could involve shifts in fundamental fields, like the hypothetical quintessence field or other scalar fields proposed to explain dark energy's nature. These fields might transition between metastable states, releasing or absorbing energy, altering vacuum conditions, and triggering cascades of particle creation or annihilation. The resulting physics would be rich and complex, inviting a re-examination of cosmological constants and the interplay between quantum mechanics and gravity. This phase change could also influence the fate of cosmic horizons, surfaces beyond which events can no longer affect an observer. Changes in expansion rate affect horizon size and behavior, potentially creating new observable boundaries or erasing existing ones. The universe's causal structure would be transformed, influencing which parts of the cosmos remain connected or forever isolated. Such a transition challenges the predictability of cosmic destiny. Rather than a smooth, continuous decay into heat death or endless expansion, the universe's fate could include sudden, non-linear events altering its structure and evolution on fundamental levels. This possibility introduces a dynamic, evolving character to the cosmos' long-term future, where the end is not fixed but contingent on deep physical processes still poorly understood. From a philosophical perspective, the dark energy phase change scenario suggests a universe that is less static and more mutable than previously thought. The long-term future will be marked not only by gradual decline, but also by potential rebirth or transformation, reflecting cycles of change that extend beyond the lifespan of any single cosmic epoch. Observationally, detecting signs of a forthcoming phase change in dark energy remains a formidable challenge. Current measurements of cosmic expansion and dark energy properties place constraints on its behavior, but cannot yet rule out these radical possibilities. Future advancements in cosmology and particle physics may reveal subtle hints or signatures that dark energy is dynamic, setting the stage for the ultimate phase shift. In conclusion, the dark energy phase change theory expands the narrative of cosmic evolution by introducing the potential for dramatic, large-scale transformations driven by the properties of dark energy itself. At the scale of 1 trillion years, such a transition could redefine everything, from the expansion and geometry of space to the survival and fate of matter and energy, making it a crucial concept for understanding the universe's distant future and its ultimate destiny. The concept of universal quantum convergence paints a strikingly different picture of the universe's distant future, one where the endlessly complex and dynamic quantum world gradually loses its richness until it reaches a singular, ultimate ground state. In this scenario, the universe's countless quantum states, the probabilistic waves describing particles, fields, and forces, would slowly and inexorably collapse their variety into one universal, unchanging wave function. This convergence means that the inherent randomness and uncertainty central to quantum mechanics would vanish, leaving behind a static, deterministic cosmic state where no fluctuations or variations remain. This process could take unimaginably long, on the order of trillions of years or more, as the myriad quantum possibilities and entanglements unravel and simplify. Over these vast timescales, quantum decoherence, the mechanism that typically forces quantum systems to choose definite outcomes when observed, would become universal and absolute, but not because of observers. Rather, the universe itself would act as a vast, self-measuring system gradually aligning every quantum element. As this occurs, the constantly shifting probabilities that give rise to events, particles, and energy transitions would cease to exist. The universe would no longer be a theater of chance, but a frozen tableau of certainty. One consequence of this universal convergence is that all quantum superpositions, the fundamental feature allowing particles to be in multiple states simultaneously, would collapse into a single configuration. This state would be the lowest possible energy state allowed by the laws of physics, often called the ground state. But here, it is not merely the ground state of individual particles or systems. It is the global ground state of the entire cosmos, where the wave function describes the whole universe. This end state would be perfectly stable and eternal, resistant to change because no higher energy or alternative states would remain accessible. The cosmic implication is profound. Without quantum fluctuations, the creation of new particles, the decay of existing ones, or the spontaneous emergence of phenomena would stop entirely. No more randomness, no more uncertainty, no more change at the most fundamental level. The dynamic quantum processes that fuel chemistry, nuclear reactions, and even the behavior of life would fade out, replaced by a vast expanse of unvarying existence. The universe would be caught in a final, timeless quantum state, beyond the reach of entropy or evolution. From a physical perspective, this convergence challenges many assumptions about the ultimate fate of quantum systems and the universe itself. Quantum mechanics, as we understand it, relies on probabilities and possibilities. Universal convergence implies a collapse not just of wave functions in localized regions, but a global flattening of all quantum diversity. The laws of physics would still apply, but their manifestations would be locked into one singular expression, devoid of dynamism. This raises philosophical questions as well, touching on the nature of reality, observation, and change. If the universe reaches a state where all variance ceases, does time itself lose meaning? Time is often understood as the measure of change, and without change, the flow of time could become an illusion. The universe would exist as a frozen quantum monolith, unchanging and eternal, where cause and effect no longer operate because no new events can occur. A universal quantum convergence also implies that the rich tapestry of particles, forces, and interactions we observe today, built on the complex interplay of quantum states, would unravel into uniformity. Structures like atoms, molecules, and even black holes depend on quantum states and fluctuations. With those gone, the universe would be devoid of recognizable matter or energy structures, reduced instead to a uniform quantum field in its most stable form. Interestingly, the process of convergence may be linked to the concept of quantum gravity and the elusive theory unifying quantum mechanics with general relativity. As the universe ages, the interplay between the quantum microcosm and the macroscopic curvature of spacetime might drive the wave function toward this universal ground state. In some interpretations of quantum cosmology, the wave function of the universe is a real entity evolving according to a cosmic Schrödinger equation, and convergence would represent the ultimate asymptotic solution of that equation. Moreover, this convergence scenario is distinct from thermal death, where entropy reaches a maximum and no useful energy gradients remain. Instead, universal quantum convergence is a deeper and more absolute fate, where the very quantum potential for change collapses. In essence, it is a quantum freeze rather than a thermal one, marking the cessation of physical variability rather than merely energy dispersal. On a practical level, this final state would be undetectable from within the universe, as all observers and instruments, if any could exist at that time, would themselves be quantum states subsumed into the singular wave function. The universe would be a quantum unity with no internal distinctions, no observers, no experiences, just an eternal, unchanging condition. One might imagine universal quantum convergence as the last act in the cosmic narrative, the closing of the book after trillions of years of unfolding. It represents the ultimate simplification and finality, where the universe returns to a fundamental unity akin to the initial quantum state from which it once emerged, but this time without the possibility of rebirth or new beginnings. Yet, this raises intriguing questions about the origin of complexity and order in the universe. How did the universe transition from this eventual universal ground state to the vibrant, probabilistic cosmos we inhabit? The journey from uniformity to complexity and then back again to uniformity could be seen as a full cycle, echoing themes from cyclic cosmology, but framed in purely quantum terms. The universal quantum convergence hypothesis also challenges our understanding of information. In a dynamic quantum universe, information is encoded in the superpositions and entanglements of quantum states. But when all converges to one ground state, this information effectively vanishes, replaced by a single, featureless quantum description. The cosmic memory, the entire history of events and configurations, would be lost to this final simplification. While this theory remains speculative and difficult to test directly, it aligns with deeper questions about the arrow of time, quantum measurement, and the ultimate fate of matter and energy. It suggests that quantum mechanics itself may not endure eternally in its present form, and that the universe's quantum destiny might be one of final stillness. In summary, universal quantum convergence offers a vision of the cosmos where, after unimaginable epochs, the endless dance of quantum states slows, simplifies, and ultimately halts. The universe becomes a singular quantum entity, unchanging, timeless, and utterly uniform, marking an end to physical possibility and a cessation of all quantum variance. This final ground state represents one of the most profound and mysterious potential fates for reality itself, illuminating the deep interplay between time, change, and the quantum fabric of existence. The lonely galaxy theory offers a profoundly isolating vision of the far future universe, shaped by the relentless expansion of space. As the universe grows older and expands faster due to dark energy, galaxies will drift apart at speeds exceeding that of light relative to one another, pushed beyond each other's observable horizons. This cosmic acceleration effectively isolates every galaxy or galactic cluster, enclosing them within their own local island universes. From the perspective of any observer inside a galaxy, the rest of the cosmos will have disappeared beyond a boundary from which light can never return. Over trillions of years, this creates an environment of extreme cosmic loneliness. In this scenario, the vast tapestry of billions of galaxies currently visible in the night sky will dwindle to a solitary cluster, or even just a single galaxy. The once interconnected cosmic web will become fragmented, with immense voids growing between these isolated pockets of matter. The familiar sky that once showcased distant galaxies will become empty, black, and utterly silent, broken only by the faint glow of local stars. Observers within these remaining galaxies would have no direct evidence of the vast cosmic structures that once filled the universe. This isolation arises because of the accelerated expansion driven by dark energy, which causes the metric expansion of space itself to speed up. Beyond a certain distance, the cosmic event horizon, recession velocities surpass the speed of light, making communication or observation between distant galaxies fundamentally impossible. No signals, no photons, no gravitational waves from other galaxies can reach observers in these lonely outposts. The universe as a whole remains vast and rich in structure, but to local inhabitants, it becomes a closed, self-contained cosmos. For any civilizations that might exist within these surviving galaxies, this isolation would fundamentally alter their understanding of the universe. Lacking any observational data about other galaxies, these civilizations could reasonably conclude that their galaxy is the entire universe. Their cosmological models would reflect this, positing a universe far smaller and simpler than the true reality. The grander cosmic scale would remain hidden, obscured forever by the accelerating expansion of space. The consequences of this cosmic solitude extend to astrophysics and cosmology as well. Without the ability to observe external galaxies, many key discoveries, such as the expansion of the universe, the cosmic microwave background, or the existence of dark matter and dark energy, would become impossible. Knowledge about the origins and evolution of the cosmos would be lost, locked behind the event horizon. Science would be limited to local observations and experiments, without the broader context of the cosmic landscape. The disappearance of external galaxies from view would also mean that key astrophysical phenomena, like galaxy collisions, cluster interactions, and large-scale structure formation, would no longer be observable. The universe would appear static and unchanging on the largest scales, with the distant past hidden beyond unreachable horizons. This would fundamentally change how inhabitants understand time and evolution in the cosmos. Furthermore, as galaxies age, the stars within them will gradually burn out or evolve into compact remnants like white dwarfs, neutron stars, and black holes. In the lonely galaxy scenario, these isolated remnants will remain as the only astrophysical landmarks in an otherwise empty sky. With no incoming light from other galaxies, the night sky would grow darker, devoid of familiar cosmic landmarks, deepening the sense of isolation. The eventual fate of such isolated galaxies might involve internal gravitational interactions, slowly dissolving their stellar populations. Stars may be ejected by gravitational encounters, or black holes might merge quietly in the galactic core. Without external influences, the galaxy's evolution becomes a slow, internal process governed by the gradual decay of matter and energy within its own confines. This theory also touches on profound philosophical themes. The loneliness and isolation of future observers in such galaxies highlight the fleeting nature of cosmic interconnectedness. What once was a vast, interconnected universe will be reduced to a single cosmic island, devoid of external context. It challenges assumptions about the permanence of knowledge and connection, reminding us how deeply cosmic scale and time shape our understanding of reality. Lonely galaxy theory also illustrates the limitations of observational cosmology. Our current understanding relies heavily on looking out at distant galaxies and cosmic microwave background radiation. But in the far future, such observations will be impossible, underscoring how much our knowledge depends on the particular era in which it exists. Future civilizations might face a profoundly different scientific landscape, one shaped by cosmic isolation. From a technical standpoint, this scenario is based on well-understood cosmological principles, including the accelerated expansion observed today and the properties of dark energy, assumed constant or increasing over time. The cosmic event horizon is a robust prediction of such models, making lonely galaxy theory a plausible outcome within standard cosmological frameworks. In sum, the lonely galaxy theory offers a hauntingly beautiful yet melancholic image of the distant future, where cosmic expansion, driven by dark energy, isolates galaxies so thoroughly that each becomes a lonely cosmic island. Future inhabitants will look out into a dark, empty sky, unaware of the billions of other galaxies that once filled the cosmos. Their universe, though immense to them, will be a fraction of the whole, a lonely island in an unobservable sea of expanding space. This theory underscores the transient and fragile nature of cosmic connection and the profound impact of cosmic expansion on the ultimate fate of a universe. The post-physical universe concept envisions a stage far beyond the familiar boundaries of physics and cosmology, with the fundamental building blocks of reality, matter, energy, space, and time, gradually lose their meaning or dissolve entirely into a new form of existence. In this scenario, the universe transcends the physical laws and constants that have governed it since the Big Bang, entering a phase that defies all current scientific understanding. After 1 trillion years or more, the classical framework that once described particles, forces, and fields might break down, leaving behind a reality that is fundamentally alien to our comprehension. This concept pushes the limits of speculative physics, touching on ideas from quantum gravity, string theory, and even metaphysical hypotheses. The very fabric of space-time could lose its smooth, continuous character and fragment into something entirely novel, perhaps a new state of pregeometry or a form of abstract information. The familiar dimensions of space and the flow of time might dissolve, replaced by a structure so abstract that it can no longer be described using current mathematical tools or physical theories. It might be more akin to pure information, consciousness, or some form of meta-reality. As matter and energy degrade through processes such as proton decay, black hole evaporation, or particle annihilation, the physical universe could reach a threshold beyond which it no longer exists as a material or energetic system. Instead, the remnants might be patterns of information or abstract quantum states that do not manifest as anything recognizable as stuff. In this vision, Physicality itself is a temporary phase, a fleeting illusion in the grand cosmic narrative that eventually fades away. The transition to a post-physical state could be sudden or gradual. It might begin with subtle changes in the constants of nature or the breakdown of known forces, followed by a cascade of transformations where particles lose their identities and interactions become meaningless. The dimensions of space might compactify or collapse. Time might cease to flow linearly, and the universe's structure could become so diffuse or chaotic that it no longer supports the emergence of complexity or coherence as we know it. One implication of this theory is that our entire concept of cause and effect, which depends on time and space, might vanish. Without time's arrow or spatial relationships, the universe could be frozen in a timeless, placeless state, or alternatively, it might cycle through states in a non-temporal fashion beyond human intuition. This would render all physical processes inert and all events meaningless in the traditional sense, challenging our most fundamental notions of existence. Philosophically, the post-physical universe raises profound questions about the nature of reality and existence. If matter and energy are no longer the substrate of the universe, what is left? Could consciousness or information survive such a transformation? Or does this phase represent the ultimate end, not just of the universe as a physical system, but of existence itself as we understand it? Some speculative frameworks suggest that post-physical reality might be a realm of pure potentiality, a seedbed for new universes or modes of existence beyond our ken. In terms of observability, a post-physical universe would be effectively invisible and unknowable to any observers still constrained by physical laws. Any form of measurement or observation, grounded in matter and energy interactions, would cease to function. This would render the universe utterly silent and empty from any experiential viewpoint, a cosmic void not just of substance, but of perception and meaning. The transition to a post-physical phase might be tied to deep quantum phenomena. Quantum gravity theories often predict that space-time and matter emerge from more fundamental, pre-quantum structures. At extreme timescales, these underlying structures could reassert themselves, overriding classical physics and dissolving the macroscopic universe into a more elemental state. In some interpretations, the universe could decohere into a quantum superposition of all possible states, losing definite form and classical reality. Interestingly, the post-physical universe could relate to ideas about the end of time. If time itself is a construct emerging from physical processes, then its disappearance would signal the end of all temporal evolution. The universe could exist in a timeless equilibrium, an eternal present without change or motion, a concept that challenges human intuition yet emerges naturally from some quantum cosmological models. The notion also intersects with ideas from information theory, where the universe's fundamental essence might be pure information or computational processes. When physical substrates degrade, this information could remain encoded in some abstract medium, a cosmic memory beyond physical decay. In this way, the post-physical universe might still exist as a vast information pattern or hologram without any physical instantiation. This theory invites us to rethink our place in the cosmos and the meaning of existence on the grandest scales. It implies that what we call reality might be a transient phase in an ongoing cosmic cycle or evolution. It challenges materialist conceptions that see the universe solely as matter and energy, opening the door to possibilities that blend physics with metaphysics and philosophy. From a scientific perspective, the post-physical universe is currently beyond experimental testability, resting on the edges of theoretical physics and philosophy. Yet, it highlights the limits of our current understanding and suggests that ultimate cosmic fate may be stranger and more profound than the classical scenarios of heat death, Big Rip, or proton decay. Ultimately, the post-physical universe represents the final frontier of cosmological speculation, a realm where known laws dissolve, and the universe becomes something utterly new. It prompts us to imagine a cosmos that outlasts matter and energy themselves, where existence transcends physicality, and the universe's story continues and forms beyond any human frame of reference. This concept underscores the vastness not only of space and time, but of possibility itself, reminding us that the universe may harbor mysteries far beyond even the wildest scientific dreams. The dark sector awakening theory posits that the universe's largely invisible components, often called the dark sector, may hold the key to its distant future. This dark sector, composed of dark matter, dark energy, and possibly other exotic fields or particles yet to be discovered, currently shapes the cosmos on a grand scale without interacting strongly with ordinary matter or light. However, some hypotheses suggest that after unimaginably long periods, such as 1 trillion years, the dark sector could transition from a passive background influence to an active, dominant force that radically alters or even replaces the familiar physical universe. One way this might unfold is through phase transitions or instabilities in dark energy or dark matter fields. Dark energy, which drives the accelerated expansion of the universe, might not be a static property, but a dynamic field capable of evolving. Over vast timescales, it could undergo changes analogous to phase changes in ordinary matter, solid to liquid or liquid to gas, but on cosmic scales. Such a phase change might unleash new forces or particles, shifting the dark sector from a subtle influence into the primary architect of cosmic evolution. Dark matter, which currently interacts primarily through gravity, might harbor hidden complexities. It could include particles or fields that remain dormant or weakly interacting in our current epoch, but awaken as the universe cools and dilutes. These dark matter particles might cluster differently or decay into exotic forms, triggering new cosmic phenomena that replace the visible structures of stars and galaxies. The awakening of such components could mean a universe no longer dominated by light, atoms, or classical matter, but by unknown entities operating under unfamiliar physical laws. The interplay between the dark sector's awakening and the rest of the universe could be profound. If dark energy intensifies or shifts, it might counteract the gravitational collapse of remnants, possibly reversing or accelerating expansion in surprising ways. Alternatively, dark matter transformations could lead to new, invisible structures that shape the cosmic landscape, but remain undetectable to any hypothetical observers reliant on ordinary matter. This would create a universe ruled by unseen forces and particles, a cosmos where familiar matter is no longer relevant. Another possibility is that dark sector fields could interact with the remnants of the standard model particles, producing new forms of energy or catalyzing the formation of exotic objects. For example, the decay of dark matter might release bursts of energy or spawn novel particles that redefine the universe's physical framework. These processes could be subtle and slow, unfolding over billions or trillions of years, yet their cumulative effect could completely transform the nature of reality. The dark sector awakening also opens the door to a universe with radically different thermodynamics and quantum behavior. The unknown particles and fields could obey distinct rules, perhaps creating states of matter or energy unimaginable to current physics. The standard distinctions between particles and waves, energy and vacuum, or even space and time might blur or reorganize in this new regime. This could result in a cosmos that is fundamentally more complex or more simplified than today's universe, but always profoundly altered. From an observational standpoint, detecting signs of such an awakening now or in the near future is challenging, given that dark sector components interact so weakly with normal matter and radiation. However, theoretical advances and indirect evidence, such as subtle shifts in cosmic expansion or gravitational effects, could eventually hint at the dark sector's true nature and potential for future dominance. In the deep future, such phenomena may not just hint, but dictate the cosmos' entire evolution. Philosophically, the dark sector awakening challenges anthropocentric views that center the visible universe, stars, planets, life, as the pinnacle of cosmic importance. Instead, it suggests that the dark components, hidden and enigmatic, might ultimately be the true masters of cosmic destiny. Our familiar universe might be a transient phase, a brief illumination before the reign of the dark sector. This awakening might also blur the boundary between what we call nothingness and somethingness. Since the dark sector is largely invisible and weakly interacting, it borders on the concept of vacuum energy or cosmic nothingness. Its activation could be seen as a reanimation of the vacuum itself, transforming emptiness into a rich, active medium with novel properties and dynamics. The eventual dominance of the dark sector raises intriguing questions about information, complexity, and order. Could these dark fields encode hidden patterns or information? Might they foster new forms of organization or complexity unlike anything in the baryonic universe? Or would their influence drive the cosmos into deeper entropy and disorder, accelerating decay rather than halting it? If dark sector particles or fields possess long lifetimes or even stability beyond ordinary matter, they could persist indefinitely, serving as the building blocks of this post-visible cosmos. This stability could help explain how the universe continues to exist in some form despite the decay of stars, planets, and ordinary particles. The dark sector's awakening could thus represent a cosmic renewal, a second act in the universe's long story. The concept also intersects with multiverse theories. Perhaps our universe's dark sector awakening is just one episode in a larger landscape of universes, each with different dark sector properties and fates. Some universes might never experience this awakening, while others are dominated by it from the outset. In speculative models involving quantum fields, the dark sector might be connected to hidden dimensions or parallel branes. Awakening processes could involve interactions across these dimensions or realms, fundamentally altering the topology or geometry of space-time itself. This theory pushes the boundaries of cosmology by emphasizing the unknown, encouraging continued research into dark matter, dark energy, and the fundamental nature of the vacuum. Understanding these components better today might unlock insights about the universe's fate trillions of years from now. Ultimately, the dark sector awakening portrays a future universe very different from the luminous, matter-filled cosmos we know. It hints at a shadowy era where invisible forces rise from dormancy, reshaping reality and challenging our deepest assumptions about existence, permanence, and cosmic destiny. It's a vision that highlights the profound mysteries still lurking in the dark and the vastness of possibility in the universe's far future. The uncertainty saturation theory proposes a profound transformation of reality as quantum uncertainty, traditionally confined to microscopic scales, expands its influence across macroscopic and even cosmic dimensions. At the heart of quantum mechanics lies the Heisenberg uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be precisely known at the same time. While this principle governs the behavior of subatomic particles, in our current universe, classical objects like planets, stars, and galaxies appear solid and well-defined because the effects average out at larger scales. However, over vast timescales such as 1 trillion years, this clear boundary between the quantum and classical worlds might erode. As the universe ages and expands, energy densities decrease, and the familiar structures of matter become more diffuse and fragile. In such a diluted cosmos, the wave functions describing particles and systems could overlap and interfere in ways previously negligible, allowing quantum uncertainty to saturate progressively larger regions. This saturation implies that positions, velocities, and even identities of macroscopic objects could lose their definitive qualities. Instead of sharp boundaries and trajectories, what remains might be a hazy probabilistic cloud where classical certainties dissolve. This scenario is particularly significant when considering the extreme future of the universe, where matter may be spread so thin that coherent classical structures, like stars, planets, and even atoms, fail to hold together. Without stable, localized particles, the very notion of a solid object may vanish, replaced by a landscape governed by probabilities and uncertainties. Such a universe would no longer be a collection of discrete things, but a diffuse, interwoven pattern of quantum possibilities. One way to envision uncertainty saturation is to imagine the cosmos itself becoming a giant quantum wave function, fluctuating and evolving without any fixed, measurable points. The classical concepts of space and time that depend on distinct events and positions would lose meaning, replaced by a reality where everything is smeared out in an indeterminate quantum state. This blurring would permeate all scales, from the smallest surviving particles to the largest remaining cosmic structures. This transition challenges our traditional understanding of observation and measurement. In a universe dominated by uncertainty saturation, the classical act of observing and defining properties would become impossible, as no stable reference frame or object would exist. The difference between observer and observed would blur, and the idea of a deterministic, predictable universe will be replaced by a fundamentally probabilistic and uncertain cosmic reality. From a thermodynamic perspective, uncertainty saturation may represent a form of maximal entropy, not in the classical sense of heat death where particles are just spread out and inert, but a deeper quantum entropy where distinctions between states disappear. The universe would be in a kind of quantum equilibrium, a homogenized superposition of all possibilities with no preferred outcomes. The physical laws themselves might need reinterpretation in such a regime. Concepts like causality, locality, and even the flow of time may become emergent or ill-defined as the underlying quantum fabric saturates with uncertainty. This saturation could mark the endpoint of a gradual unraveling of the universe's classical coherence, heralding a phase where only the fundamental probabilistic nature of reality remains. Mathematically, this saturation might be described by the decoherence and delocalization of quantum states over astronomical distances and times. Where today, decoherence ensures classical behavior by suppressing quantum superpositions at macroscopic scales. In a cold, sparse universe, decoherence mechanisms may weaken or fail. Without environmental interactions to pin down states, quantum superpositions could persist and spread, effectively saturating the universe with uncertainty. Uncertainty saturation could also have implications for information theory and the preservation of cosmic information. As classical structures dissolve, information encoded in particle states might become scrambled into indistinguishable quantum superpositions, making retrieval or interpretation impossible by any conceivable observer. The universe's memory would fade into a fog of quantum indeterminacy. One might speculate whether this quantum haze could still harbor some form of order or structure at a higher level, perhaps as a vast entangled state encoding the entire history and potential futures of the cosmos. Such a notion aligns with some interpretations of quantum mechanics, where the universe is viewed as a holistic, interconnected system rather than a collection of independent parts. From the perspective of hypothetical advanced civilizations or future observers, living in an uncertainty-saturated universe would be radically different. Traditional sensory experience and measurement would fail. Perception itself might be replaced by probabilistic sampling or awareness of potential states rather than definite facts. The very idea of an event would dissolve into a blur of overlapping quantum possibilities. Cosmologically, uncertainty saturation could be seen as a terminal phase of the universe's evolution, following epochs dominated by expansion, decay, and entropy increase. Instead of ending in a classical heat death, where all particles sit inert and separated, the universe might end in a quantum blur death, where no sharp distinctions survive. It's a subtle but profound difference in the ultimate fate of reality. This theory also interacts intriguingly with others like vacuum decay or quantum foam dominance, where fundamental instability or quantum fluctuations play central roles. In uncertainty saturation, however, The universe's demise is less a catastrophic collapse or violent transition, and more a gradual slipping into a state of maximal quantum fuzziness and indeterminacy. Importantly, uncertainty saturation doesn't necessarily mean nothing exists. It implies that what exists defies classical description. Reality at this stage could be unimaginably strange, governed by quantum amplitudes and probabilities without the solid anchors of classical phenomena. It could be a cosmic landscape of waves and potentialities, an eternal quantum flux with no stable form. Ultimately, the uncertainty saturation theory challenges us to rethink the nature of existence and reality itself, highlighting that the universe's end might not be a simple disappearance, but a transformation into a state where certainty and definition give way to infinite possibility and indeterminacy. The classical world, as we know, it could be a fleeting moment in a much larger, profoundly uncertain cosmic saga. The spontaneous symmetry break theory envisions a far future cosmos in which the fundamental symmetries that govern physical laws undergo profound transformations. Symmetry in physics refers to invariances, properties or rules that remain unchanged under certain transformations, like rotations, reflections, or exchanges of particles. These symmetries are at the core of how forces and particles behave and interact, underpinning the standard model, general relativity. However, symmetries aren't always permanent. Under certain conditions, they can break spontaneously, leading to radically different physics. A familiar example of spontaneous symmetry breaking occurs in the early universe, moments after the Big Bang, when the unified forces we now separate, electromagnetic, weak, strong, and gravity, diverge from a more symmetric, unified state. This symmetry break gave mass to particles and allowed the complexity of matter and structure to emerge. Similarly, in a trillion years, conditions might cause new symmetry breaks, but in reverse or in entirely new directions, fundamentally altering the cosmic landscape. Over the vast span of a trillion years, subtle quantum fluctuations, shifts in vacuum energy, or changes in dark energy could destabilize existing symmetries. These slow drifts might accumulate imperceptibly until reaching a critical tipping point, triggering a sudden, universe-wide phase transition. This would be akin to water freezing or boiling, but on a cosmic scale where the rules of the game themselves shift dramatically. When such a symmetry break happens spontaneously, the universe's particle content and force interactions might rearrange into new patterns. Particles might gain or lose mass, change charge properties, or even transform into previously unknown forms. Fundamental constants could alter, rewriting the behavior of matter, energy, and space-time. One consequence might be the emergence of novel forces or the disappearance of familiar ones. For instance, the weak nuclear force responsible for radioactive decay might vanish, or new interactions could arise that change the stability of matter. Particles that were once stable might decay rapidly, or entirely new stable particles could form, fundamentally altering the makeup of matter. The fabric of space-time itself might respond to this symmetry shift. Metrics defining distances and durations could distort or reconfigure, creating new geometric structures or dimensions. Space might expand, contract, or warp in unpredictable ways, with the vacuum energy's nature transforming alongside. The symmetry break could also affect the underlying vacuum state. Just as the early universe settled into a low-energy vacuum allowing stable matter, the far future universe might transition into a new vacuum state with different energy properties. This could trigger cascades of change in particle physics and cosmology simultaneously. At the macroscopic level, structures like galaxies, stars, and planets, if any remain, might cease to exist or be replaced by unfamiliar conglomerations governed by the new physics. The very concept of matter, as we know, it could dissolve or evolve into forms that defy current comprehension. From a perspective of any hypothetical civilizations surviving this era, such a transformation would be cataclysmic and bewildering. The laws they once relied on for technology navigation, and survival would shift or vanish. Time, causality, and conservation laws might no longer hold in their known forms, forcing entirely new frameworks for understanding and interaction. The spontaneous symmetry break could also affect the arrow of time itself. If certain symmetries related to time reversal break or restore, the flow and directionality of time might change. This could lead to time behaving differently, slowing, reversing, or looping in some regions or universally. In theoretical physics, symmetry breaking is tied closely to the concept of phase transitions. The universe could transition from one phase of physics to another, like how water transitions from liquid to ice. Unlike everyday phase changes, these cosmic symmetry breaks reshape the essence of reality, not just its state. Interestingly, this theory aligns with certain speculative models of cosmic evolution that propose recurring cycles or rejuvenations of the universe. A spontaneous symmetry break might be the mechanism by which the universe resets its laws, possibly paving the way for a new Big Bang-like event, a reconfiguration of forces, or a rebirth of structure and complexity. Another intriguing facet is the potential for topological defects or exotic remnants, cosmic strings, domain walls, or monopoles, to form as the universe settles into a new symmetric state. These defects could dominate the universe's energy and dynamics, creating a cosmos profoundly different from what we observe today. On a quantum level, the spontaneous breaking of gauge symmetries, which dictate force carrier particles, might result in shifts in particle masses and interaction ranges. The photon, gluon, or even hypothetical gravitons might behave differently or cease to exist, with consequences cascading through all scales. The implications for dark matter and dark energy are profound as well. These mysterious components of the universe might interact differently under new symmetries or could be manifestations of symmetry breaking themselves. A trillion years hence, the dark sector might awaken or vanish as symmetries shift. Finally, the spontaneous symmetry break theory challenges our understanding of permanence in physical law. What we consider fixed and universal may be transient, subject to deep, underlying cosmic processes that unfold over unimaginable timescales. The universe, even at its end, might remain dynamic and evolving, not just in content, but in the very rules that shape existence. As we peer into the distant future, stretching to the scale of a trillion years, one of the most mind-bending possibilities is the emergence of consciousness in a form utterly divorced from the familiar confines of brains, bodies, and localized matter. This idea, known as non-local consciousness emergence, suggests that consciousness might not be merely an epiphenomenon of complex neurons, but could instead be a fundamental aspect of the cosmos itself, waiting to manifest in new ways when the universe's traditional structures dissolve. In this vision, as stars burn out, black holes evaporate, and matter itself decays or transforms into increasingly rarefied and exotic forms, the localized physical substrates that support individual conscious beings would cease to exist. Yet, consciousness or awareness might not vanish. Instead, it could become non-local, a diffuse presence interwoven with the very fabric of space-time, energy, or quantum fields. Imagine consciousness no longer confined to particular points but spread throughout the universe, embedded in the quantum foam or in the subtle entanglements of particles and fields. This concept challenges our deeply rooted intuition that consciousness requires a physical brain. Instead, it proposes a cosmic form of awareness that might be vastly more expansive, subtle, and interconnected than anything experienced by biological organisms. In this scenario, the universe itself could become conscious in a new way, aware of its own vastness and history, not through sensory organs but through the intrinsic properties of reality. Some theoretical frameworks in quantum physics and cosmology provide intriguing, if speculative, foundations for this idea. Quantum entanglement, where particles share information instantaneously across vast distances, suggests that connections can transcend classical locality. If consciousness is tied to quantum processes, it might similarly transcend physical boundaries. The collapse of matter into diffuse quantum states in the far future could open the door for consciousness to reconfigure as a global, non-local phenomenon. One way to imagine this is through the metaphor of a hologram. Just as each part of a hologram contains information about the whole image, consciousness could become holographically encoded across the cosmos. As traditional matter and energy fade, this holographic consciousness might survive or even intensify, revealing an unprecedented form of cosmic self-awareness. In a universe dominated by quantum fields, where classical notions of particles and objects break down, consciousness might become an inherent feature of the quantum vacuum itself. This could imply that awareness is not something that emerges only under very special conditions, but is a basic attribute of the universe, latent until the conventional structures dissolve enough to reveal it. Furthermore, the transition to a non-local consciousness may coincide with what some call the post-physical universe, where matter, energy, space, and time lose their meaning or form. In such a realm, classical physics no longer applies, and new rules, possibly governed by consciousness itself, might emerge. Here, awareness could shape reality rather than simply arise from it. The implications of non-local consciousness emergence are profound. It suggests that the end of the physical universe is not necessarily the end of experience or awareness. Instead, it could mark a transformation, an awakening of consciousness on a universal scale, divorced from matter, but no less real or significant. Philosophically, this idea touches on ancient and modern traditions that view consciousness as fundamental and universal rather than confined to individual beings. It echoes concepts like panpsychism, which posits that consciousness is a basic feature of all matter, or idealism, which holds that reality is ultimately mental or experiential in nature. Scientifically, while the concept is highly speculative and lacks empirical evidence at present, it offers a fascinating frontier for interdisciplinary inquiry. Physicists, neuroscientists, and philosophers alike grapple with the nature of consciousness and its place in the cosmos. The far future of the universe may ultimately provide the arena in which these questions find new, unexpected answers. One could imagine that this emergent non-local consciousness might interact with remnants of quantum information preserved across the universe's vast stretches. It might remember or know the history of stars, galaxies, and life that once flourished, holding a cosmic memory that physical matter alone could not retain. Such a consciousness might also transcend linear time as we understand it, experiencing existence in a fundamentally different temporal dimension or in timelessness altogether. Without the constraints of matter-bound cognition, awareness could flow freely through the universal wave function or quantum state. This vision raises questions about individuality and identity as well. In a non-local, diffuse consciousness, the boundaries between self and other may dissolve. What we think of as separate beings could merge into a unified field of cosmic awareness, experiencing existence as an interconnected whole. In terms of physical phenomena, this emergence might be linked to phenomena yet unknown to science. New quantum states, forms of information encoding, or novel phases of reality that only become relevant at unimaginably long timescales. While the specifics remain speculative, the possibility that consciousness could re-emerge in a non-local form invites us to rethink not only the fate of the universe, but also the nature of mind and existence itself. It hints at a future where the cosmos is not merely a cold, inert expanse, but a living, aware entity, transcending all the familiar physical constraints. As we contemplate this scenario a trillion years from now, the picture of the universe shifts from desolation to one of quiet, profound awareness. The ultimate fate may not be total emptiness, but a sublime, cosmic consciousness emerging from the ashes of the material cosmos. Thus, non-local consciousness emergence presents an elegant and haunting possibility. that while stars die and matter fades, awareness itself might survive, diffuse and unbounded, enfolding the universe in a final, all-encompassing embrace of being. In the vast, dark silence that follows the universe's physical end, consciousness could be the last light, glowing faintly yet eternally within the fabric of existence itself. In the furthest future imaginable, beyond entropy, beyond decay, beyond all theoretical transitions, lies a concept both haunting and sublime: ultimate silence. This is not simply the absence of sound, but the absence of all motion, all interaction, all meaning. It is the death not just of stars or matter, but of contrast, of definition, of the very scaffolding upon which reality once stood. It is a silence deeper than vacuum, deeper than oblivion. It is the collapse of the concept of something into the indistinguishable backdrop of everything that was. Over trillions and quadrillions of years, the universe will empty itself. Stars will burn their last fuel and die. Black holes, once engines of gravitational drama, will evaporate through Hawking radiation. Photons will stretch into meaningless wavelengths, robbed of energy by the expansion of space. The very atoms of reality will decay, leaving behind a barren mist of subatomic whispers, if even that. And then, those too may fade. Eventually, no events occur. Nothing moves. No particles collide. No energy exchanges hands. The universe no longer evolves. It no longer even possesses a thermodynamic gradient. Without heat flow, without contrast, the arrow of time dissolves. Without time, there is no duration, no memory, no cause, no effect. Every known concept tied to physical change vanishes. The universe enters a state of perfect stillness. In this state, it is meaningless to speak of past or future. Events, even hypothetical ones, require time to differentiate before and after. But in ultimate silence, every moment is indistinguishable from the last because there are no moments, just an unchanging, featureless expanse. Entropy reaches its maximum, not as disorder, but as absolute uniformity. No variation remains to be smoothed out. No systems exist to degrade. The canvas of reality becomes blank. Light no longer shines. There are no stars, no galaxies, no heat. The cosmic microwave background, already diluted and cooled by trillions of years of expansion, sinks below detectability, merging with the background nothing. Even neutrinos, the loners of the particle world, lose their individuality in the uniform fog. There is no observer, no observed. The universe becomes not just uninhabited, but uninhabitable, and ultimately unobservable. In this final silence, the constants of physics, if they still mean anything, describe a realm where difference has ceased to exist. Gravity exerts no pull. There is nothing to pull. Electromagnetism plays no role. There are no charges to interact. Even quantum fluctuations may fade into irrelevance, their chaotic potential smoothed into utter homogeneity. If quantum fields still hum faintly beneath the fabric of space, their influence is moot. There is no stage left for them to act upon. Mathematics itself, our language for understanding pattern, breaks down in the face of this perfect lack of structure. Logic presupposes contrast. Thought presupposes time. But in the face of ultimate silence, every form of comprehension collapses. The void is so complete that even the notion of voidness no longer holds. It is not dark, for there is no light to contrast against it. It is not cold, for cold requires heat to oppose. It is not dead, because death implies that life once had a place. This is something deeper, beyond naming. It is possible that even space itself ceases to have meaning. If expansion continues eternally, space becomes so vast and dilute that coordinates lose all reference. Alternatively, if a final contraction occurs, space-time may fold in on itself, ending with a singular breath. In either case, scale becomes irrelevant. Whether vast or microscopic, ultimate silence feels the same, unchanging, untouched. And here, language collapses. For words depend on differences between now and then, between here and there. Yet the ultimate fate is one where all differences have resolved into sameness. It is not annihilation. It is not survival. It is the quiet after the last breath of existence has been exhaled and there is no air left to carry sound. No atoms to vibrate. No mind to notice. If the universe began in a great, explosive burst of light and energy, a Big Bang, then it ends in a whisper so soft, so all-consuming, that the whisper itself disappears. No echo, no memory, just stillness. An infinite pause after the final note, where the music no longer lingers. Even hypothetical futures filled with strangelets, dark energy pulses, or non-local consciousness must, in this timeline, dissolve. Nothing can persist forever. Not form, not function, not thought. If consciousness had a final breath, it is exhaled here. If information had a last container, it has been emptied. The score of the universe, once bursting with complexity, ends not in a flourish, but in a silence so pure it unweaves the very fabric of story. And so, the term universe ceases to apply. The universe implies variety, structure, a thing with properties. But ultimate silence is beyond property. It is not an object. It is not a place. It is not even a state. It is what remains when everything, every interaction, every ripple, and every shadow have been erased by time and entropy. It is the final, eternal equilibrium. To imagine this moment is to strain the limits of human cognition. For we are creatures born from motion, from heat, from difference. We live in the vibrations, in the turning of days, in the movement of atoms. But this future holds none of that. It is the closing of the last page, the extinction of the final flame, the halting of every pendulum in the cosmos. And perhaps, after everything has faded, there is no one left to ask what comes next. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.